Hello, everyone. I hope you can all hear me well. My name is Matusz Kasparik, and I'm excited to welcome you to the second day of our GeoPython and Python machine learning conference. We have another day full of exciting talks ahead of us, and it is my pleasure to introduce the next speakers to you. But before I do that, please note that you can ask questions related to the talks either here in the Zoom Q&A section, or you can post your questions in our Discord chat. And without further ado, let me introduce you our next speaker, who is Ankit Mahato. Ankit is a polyglot programmer and a die-hard Pythonista. He's also an active contributor to open source projects, namely Numba and Titus2. I'm sure he will tell you more about that. And he's currently a core developer to the portable format for analytics project for Python 3. In his talk, Ankit will talk about model exchange formats that are about to bring some democracy to the model development process. And so I leave my words to Ankit. You can start, Ankit.
Hi everyone, I'm Ankit. So just wanted to quickly check if is my screen visible to everyone, the slides?
It's good, Ankit.
Yeah. So hi everyone. Today I'll be talking about democratizing machine learning model development process, and just a bit about myself. Metis quickly, briefly introduced me, and I think that's what I wanted to talk about myself. So I'm a contributor to the Number project, and also Titus 2, which is a portable format of for analytics implementation for Python 3. And I've been working in the industry, analytical industry, for around 6 years. I started off as a data scientist, then move on to become a product manager, shipping product called as Dblytics, which has around 600 functions. And so I've been basically working towards the model deployment process for a lot of companies, and how to basically make the model development and deployment cycle faster. So that's my core focus for the years. So we'll quickly start with the talk. So let's start with the first thing that I'd like to talk about, which is evolution of analytics. So I'll be talking about how analytics has evolved over the past years or decades, let's say, and how we have brought together analytics closer to the data source. So when we first started with analytics, it was basically dedicated machines. So we had dedicated machines like dedicated servers, analytical servers like SaaS servers, where people will go and perform analytics, run their codes on the data and get the results. Then over the past 2 decades, the cloud has emerged, and people are now running basically running on public and private clouds. So all their analytics have been run on the public and private clouds. Then came the era of fog, where basically you, for example, let's take an industry. It has a lot of sensors and a lot of robotics, and basically different kinds of sensors. Yeah. And to manage them and to basically interact with these sensors and they basically run the model. Usually they have a network, internal private network, where there is a single analytical server, which is called as a fog. So this server is not connected to the cloud, but locally it is like a cloud for the local group of sensors. So that is called as a fog. So the fog emerged, where people were started bringing the analytics closer to the source of the data capture process. And today, now we have completely moved to the edge. So a lot of the new devices have analytical engines embedded in them. And so basically we are trying to capture the data and process them at the source of data capture. So that's called as an edge. So this is how the analytics has moved towards. And let's move on to the next segment. And a major reason of moving towards the edge was that today it is approximated that around there are around 50 billion connected devices. So these many devices, you cannot capture, send the data to the cloud and basically process them. So bringing the analytics closer to the edge enables these 50 billion devices to process the data and basically run the models. So now let's talk about what is the need of edge analytics. So why is the cloud no longer sufficient? The first and foremost thing is speed. So when you perform analytics at the edge, there you gain the speed that there is no latency. You are not transferring any data to the cloud and waiting for the data to be processed and then getting back the results. You are processing data at the source itself and deriving some valuable insights, which is basically we perform analytics to get some valuable insights, and that can be done at the source itself. So that's why you gain a lot of speed. So that's why you move towards the edge. And next thing is cost. Running these cloud servers puts a lot of load on the data transfer process. As you can see, there is a cost of data transfer involved whenever you deploy your models on the cloud. So it saves a lot of cost because you can process the data at the source itself, and basically save only the valuable insights instead of saving the entire data, which will take a lot of space also on the cloud, and also a lot of network and bandwidth cost. So you save a lot of cost by processing data at the source. Again, next thing is connectivity. So basically a lot of countries, developing countries, they don't have the internet connectivity which is so good that you can transfer gigabytes of data to the cloud. So and also there are a lot of locations, remote locations, where you want to deploy analytics. For example, this windmill that you see, so there are islands which have windmill, and they do not possess the capability to basically connect to a network and transfer the data to the cloud. So you want to keep your analytics. So for example, for this windmill, you can have uh, basically wind turbine. You can have a model which is deployed locally, which will process the current state of all the health of the wind turbine, the health, the other stats basically, and basically tell you that okay, the it is functioning really well, and you and or if you need to do some maintenance to as some parts are failing. So these things can be processed locally, and that's the reason why basically the kind of low connectivity can lead to companies and firms explore the model deployment process at the edge. And last but not the least, privacy and security. This is one of the major concerns that a lot of data which basically the users want to know that okay, are their data going to be transferred to the cloud and stored there for how long, and basically what valuable insights are the companies deriving from that data, are they selling that data. So these are some important privacy concerns which users nowadays have, and they want their data to stay with themselves. So a lot of companies are pushing towards moving towards the edge and putting their analytics model on the device itself, so that the data is private and secured, as they are not transferring the raw data to the cloud, and only the valuable insights, as in what is the health for example, for products like Fitbit or Apple Watch, only the healthcare stats, like is the user facing is there some health issue which is going to basically haunt the user later on by processing his blood oxygen level or basically ECG, instead of transferring the entire raw data. So this privacy and security concern is one of the major reasons why companies are pushing towards the edge. So let's see some of the let's elaborate on some of the use cases. We all are familiar with the rise of basically autonomous vehicles, and so transportation sector is one of the core sectors where analytics is performed at the edge. As you can see, there are a lot of sensors like long range radar, lidar. There are cameras which are generating tons of images, capturing tons of images. Then there is different types of range radars, and approximately 1 Gbps of sensor data is generated by an autonomous vehicle, and this such huge amount of data is not, it is not possible to transfer it to the cloud and then process, and by the time they receive some actionable insight, uh, it is too late. So that's why you have to deploy cutting edge model at the edge, which is in the vehicle itself. So this is one of the major sectors which is using it. Then in healthcare, as I discussed, Apple Watch, Fitbit, these kinds of devices, they now have their analytical engine built in the device itself, so that it can give the user, it can give a quick feedback to the user that, okay, is he at the danger of an heart attack, or is there any issue with the health? So there are a lot of other devices also which are available in this sector, which process the data, raw data quickly, and inform the user about any actionable insights. And obviously there is manufacturing. So there was first industrial revolution, second and third industrial revolution, and right now there's another revolution going on, where a lot of industries, manufacturing sector, and also warehouses of e-commerce, they are deploying a lot of robots and basically systems which have analytics inbuilt in them, so that they can perform basically the tasks and the processes efficiently, and increase the throughput of the firm. So it is majorly used in manufacturing nowadays. So now let's move ahead to the analytics life cycle. So we will talk about what is the analytics life cycle, and it is basically basically any analytical process can be incorporated into this life cycle, which starts with identifying the problem. So basically you identify the problem, what is the problem that you're targeting, and then you access the relevant data, whether the data resides in a SQL database, or it resides in a simple CSV file, or some other basically on the over the web API. So you go ahead and access the data, then you explore the data, do some initial exploration of the data using some of the toolkits in Python. There are some toolkits in Python which help you do that. You do some initial plots and calculate some initial statistics and explore the data. Then you pick the right variables, features, which are relevant for your model building process through filtering and transformation of the data. Then you actually go ahead and build the model. This is something which excites everyone, which is building a model and basically seeing their entire process in action. Then you evaluate the model. We use a lot of methods to evaluate the model, like uh, k-fold methods and other methods, accuracy, to evaluate the model. And then we then starts the process of actually using the developed model to get some actual insights by exporting the model, deploying it, then monitoring the model, how it is performing. Is it performing as expected on real life data sets of the users? Is it evolving over the time? There might be cases where your model is degrading with time, it is not up to the mark, so you monitor the results. And then you manage the model, basically versioning, model versioning, how to update a new model. And basically those parts come under the managing model management part. And then after managing models, monitoring the result, you can stumble upon a new problem, and the cycle continues. So this is an important analytics life cycle, which defines all the key aspects involved in starting from identifying the problem to deploying the model. So most of the talks you might have started with identifying the problems, and finished it off with evaluating the problem. But what happens after it? So okay, you developed a model. It is giving you 99% accuracy on the test data set. Great. Now what are you going to do with it? How are you going to deploy it? So these are some of the key questions that we need to ask, that how it actually happens in real life and in firms. So then we come to the next part, which is democratizing model deployment. So what do I mean by it? Is basically democratization of model deployment is giving the choice to the model developer, that how he wants to deploy his model. So that part, whether he wants to deploy it using a particular infrastructure, or a particular framework. So giving that choice to the developer, it's called democratization of model deployment. And let's take a hypothetical company X. In that company, there's a data science team, and there are data scientists spread across the globe, and some are proficient in might be proficient in TensorFlow, scikit-learn. Some might be proficient in RS2 AI. Some might be proficient in Keras PyTorch. So, and some might be proficient with some Java libraries like Vika and Spark ML. So data scientists have their own core competencies in terms of, or preferences in terms of programming languages, toolkits, and frameworks through which they develop their models. And suppose these four data scientists, they come together uh, to solve a problem. They develop individual models, M1, M2, M3, M4 as seen, and then send it to the basically the IT DevOps team to deploy it. So what happens next? So this is what happens. People wait. They are like, okay, why isn't my model deployed? So the DevOps person says that we are coding it in C++. Then the developer says that, okay, we can just containerize it and orchestrate. And the DevOps team is like, no, we cannot do that. And basically, we all have gone through conferences a lot of and heard it in tons of conferences that why don't we just do containerization and orchestration? So this is a major sector which is growing, and a lot of people talk about it. Okay, like, why don't we do it for our company? Why don't we just develop it and ship the basically containers? So so there are various architectures that comes into the picture. Traditionally, firms, they have monolithical servers where they have basically a single deployment framework, a production server where they deploy their models. Nowadays, the trend has been moving towards microservices, where basically that's what I talked about. Basically, containers. Each developer will basically create his own container, shape his own app in that container, and that will be deployed on the cloud. And another growing trend is using functions. Basically, this trend has been there growing for not bulk processing, basically, but small things or small function snippets, or basically single, for example, AWS Lambda, Google Cloud Functions. You might have deployed some models on these frameworks using serverless functions, where the entire basically pang of maintaining a server does not exist, and you transfer it to the basically the IT part and the server part to the companies like Amazon or Google. So basically has been a growing trend. But does a developer have control over this framework? No, he doesn't. Basically, it's the firm's decision, and they set up their basically deployment framework that, okay, this is the architecture that we are going to follow. So at times, a developer is basically bound by that architecture that the firm has decided, and at times he's even bound by the toolkits that the firm has decided. So these are the things that stop a developer from taking that call on model deployment process. And also, and a major, and it's not like that the firms basically are happy with it. It's just because there are instances where you need specialized IT ops practices to basically support these new frameworks like containers and microservices. Uh, and a very good example is, for example, is Netflix. They have developed an entire field of chaos engineering to basically handle the testing and deployment on microservices. So you need specialized IT ops people to do that, and it is not possible for each and every firm to hire such specialized talents. So keeping that in mind, so we still have that question, that then what's the way forward? How can a user use the choice of his toolkit and still deliver and develop a model and ship it? So so that's what transitions us to the next step. So deployment is not possible, but do we still have a method through which we can democratize the model development process at least? Yeah, we do. Suppose we have a model interchange in between M1, M2, M3, and M4. All these four models, they were converted into a form which can be easily deployed. That would have definitely solved our pang. So basically, now the developer was free to use the toolkit of his choice, and still he can develop cutting edge models and ship it easily. And for the ops people, it would be very easy to deploy these models because they are given in a standardized model interchange format. So once the analytical models have been created by the team, the process to operationalize them is lengthy and labor intensive. Hence, there are need for open standards to basically open standards for model interchange through which they can communicate with the ops team and ship and deploy the model as soon as possible. So this brings us to the next segment, which is, so what's the way to save and share a model? So how should we go about it? Once we have developed a model, how should we go about saving and sharing them? So to start with the machine learning models, let's take a few steps back and see how we are doing this data exchange and serialization for actual data. So we are all familiar with CSV format. It is the one of the most popular formats used for exchanging data, and we have seen how robust it is, and a lot of be it any toolkit, it has the inbuilt capability to read CSV files and process them, and a lot of other formats emerged since CSV format was tabular in nature. A lot of formats emerged which can handle unstructured data like XML, JSON, YAML. So JSON is one of the most used format for unstructured data, and it is the data of the web, data exchange format of the web. We all our APIs and all our basically apps, they use JSON. Web apps, they use JSON to transfer data and transmit data and process them. So it is one of the, it has widespread support. It is human readable, but there are disadvantages of JSON. Basically, it has limited data types, and there are some non-supported data types which are converted to string, and this has to be again dealt at the basically execution front, where you have to process such non-supported types. But so that was about talking about data. But but data is just a part of it. How do we actually serialize data structures and code objects? So data structures are like complex data types, and actually data structures which a programmer implements for his particular model. And code objects are like snippets of code which can be executed for the scoring engine part. So how do we do that? So basically, in programming, in a particular programming language like Python, Java, Ruby, R, we have some inbuilt serialization there. We all have used the pickle format, basically pickling Python code, and there is Java serialization there. Then there for R, there is RDS and RDF formats. So these are built-in serialization format, but and it supports complex types and code objects. But there are disadvantages of using it too, as they can be malicious if they come from untrusted source. And also there is language locking. You cannot create a pickle and the pickle file and then read it using Java, or create a RDS file in R and then process it in basically Python. So a lot of basically, so the language for processing such uh, serialized formats is fixed. So that is one of the major disadvantages of these inbuilt serialization methods. But what has happened is, due to big data, a lot of new serialization formats have emerged, which are efficient, and they are language neutral. So and also they are platform neutral. So some of these formats, for example, a very famous format is SDF5, and then there are new age formats like Avro, Protoprof, Thrift. So these are some of the new formats which has emerged due to big data, and they are language neutral and efficient. So we can look into such kind of format to actually create our model interchange format. And this is the current landscape of the model exchange serialization in machine learning, which is going on. For example, if you are using scikit-learn or you are using TensorFlow or R to develop a model. In scikit-learn, you can create a pickle file or a joblib. In Keras, you can export your model as H5 format. In TensorFlow, you can do it as basically flat buffer, saved model format. Or in R, you can create an RDA format. But a major issue that is undergoing is this these libraries and this entire field itself is evolving so rapidly that if you are stuck with a framework which sudden, for example, Keras last year, Keras suddenly said that okay, it is now dropping all supports for other frameworks and going by TensorFlow itself. Then Theano also said that they are deprecating, basically they are no longer in active development. Caffe2 also said that okay, we are now shutting down and everything has to be shifted into PyTorch. So the whole field is evolving so rapidly that you cannot afford to get stuck with a particular format or a particular framework, and you need a language neutral, framework neutral way of saving a model so that you can ensure they can be reused in the future. And so there is a need for developing standards, and this XKCD comic basically encapsulate how standards proliferate. And basically there are situations where there are competing standards, and then they say that okay, we need a new standard, and then there are 15 competing standards. So this is one of the reason standards are very tricky, and you need to ensure that okay, there has to be a momentum towards a particular standard, and so that basically you ensure that okay, this should be the industry standard. So there are
3 minutes left, Ankit.
Yeah, just a few slides left. Yeah. So there are few interchange formats like PMML, NNEF, Onyx, and PFA. So these are some of the interchange formats which are currently in development, and people are and there's an entire specification developed for them. Then there are a few formats for which there is no specification. So so we will not talk about them since only with the specifications and a particular majority of people going towards a particular standard, that is important. So one such standard is PMML, where you can use different frameworks and export their model using different libraries, and then create a PMML file which can be deployed. Another standard is like PFA, in which I also work. So you can create a model in R or Python, and then you can export it into PFA and ship it into Java, deploy it in Java or Python servers. And then there is an Onyx. So this is a very latest standard which has gained a lot of industry traction. So so basically in Onyx, it's a standard for exchanging neural networks. So you can develop a neural network model using any of the frameworks and then ship it as an Onyx file, which can be deployed on any hardware or software. Basically, so this Onyx format is gaining a lot of traction. So you can see how it works. So if you maintain individual exporters and scoring engines for each and every format, there are you have to maintain around n square libraries. But using a standard Onyx interchange format, you just need to maintain one library for score, basically for scoring the model, and each and every framework, they will just export the model into that particular Onyx file. So another competing is NNEF, which says that it is complementary to Onyx, but actually it is not. It is one of the competing standards, and it has not gained that much traction. So Onyx has been the go-to framework for deploying for exporting deep learning models and deploying them at the edge. So I'll just show you a bit about Titus 2. So this is an example framework library that I developed, and this basically is based on a PFA format. And just to show you how this exchange format looks, let's take a look at it. So yeah, So you can, for example, let's say a particular very simple model. So there's a very simple model which is expressed in the form of a JSON. You can have an input data type, an output data type, and the action that you want to perform on for that particular input to get the output. A complex example is here where basically you have different types. This is a complex structure, which is a planet which has a record data type. Basically, you have different, it's like representing a row of data. And then you can perform, you specify the input as a complex type and the output as another complex type. And you can do all the computation in the action part and then get the result. So this is a sample PFA data, basically data interchange file. And to basically just, you can have a quick look at PFA, which is readable. Onyx, basically Onyx files are not readable. So PFA is a good example to actually get a readable way to look how model interchange actually happens. So you can see the PFA specification in the PFA part, that you have an input, output, and the actions that you want to perform on the data. Then you have memory, also shared memory, and how you keep a track of the new inputs and the current output. So you can have a look at this part. And yeah, if you have any question, just post it on our Discord group, and yeah, we are good to go.
Okay, thank you, Ankit, very much for this exciting talk and very important topic. I'm just checking if we have any pressing questions in our Q&A, but I don't see any. And since we are already a bit over time, I would suggest that people reach out to you over Discord and ask you questions there.
Yeah.
And thank you very much again. And I will now introduce our next speaker.
Thank you, everyone.
Who is Marty Bosch. Marty Bosch is a PhD student in the Urban and Regional Planning Community team of the École Polytechnique Fédérale de Lausanne. Sorry for my bad French. In his talk, Marty will talk about how you can simulate urban heat islands with remote sensing, air temperature data, and cadastral data. So I give my words to Marty, and you can start. Excuse me, Marty, we can't hear you. Maybe you should turn up your microphone a bit. Marty, we are still getting very noisy sounds.
Okay, now it should be working well.
Yes, now it's great.
Okay, sorry about that. Okay. So if I can go back now to the where I'm sharing the screen here. All right. Okay, so sorry for this inconvenience. Like Matus introduced, I'm gonna talk about how we can use a bunch of Python libraries and data to simulate urban heat islands. So I'm gonna briefly talk about the motivation. I guess we are all aware of what urban heat islands are, but basically when we change natural surface to urban surfaces, it modifies the energy and water balance processes and the movement of air, which often in many climates leads to warmer temperatures in the city center than in the rural surroundings. So this is sort of the definition of an urban heat island, and just a plot to illustrate it. So basically, we have consistently observed for the later, these recent years, we have consistently observed higher temperatures in city centers than in surroundings or even parks. So there are two main ways in which we measure urban heat islands. The first one is the canopy urban heat island. So this is what we measure with air temperature. Usually when you see the weather forecast, they talk about the temperature stations, that this is the temperature measured at 2 meters above the ground. This is what we usually hear. And there's also the surface urban heat island, because since there's a lot of open source remote sensing data, they have developed methods to compute land surface temperature from the sensor measurements in satellites. So we have a lot of data about land surface temperature, which is why a lot of the research, most of the urban heat island research that studies the spatial patterns of urban heat islands is based on surface temperature. However, the thing is that air temperature is closer than land surface temperature to what we feel. We feel the air temperature. Land surface temperature can be way hotter depending on the surface, or way cooler. So this is why if we can simulate the air temperatures, we can also better estimate the effects on energy demand for air conditioning, effects on health, and so on. So this is why we decided to use this model called the InVEST Urban Cooling Model. Basically, it's part of a platform that it's called Integrated Valuation of Ecosystem Services and Trade-offs, which is a suite of models that model the formal definition would be goods and services from nature that sustain life and fulfill human life. So in other words, basically what the benefits that we can get from nature. So we can get shade from trees, or we can also get trees maybe can protect us from floods and so on. These are these ecosystem services, and this is what the InVEST platform models. Another key aspect of the InVEST platform is that all the models are spatially explicit, which means that the inputs and outputs are maps. So I'm not gonna give you a value for Lausanne, just a number. I'm gonna give you a map of the temperature. Or if I was evaluating the risk of floods, I would give you a map with the risk of floods, not a number that evaluates that. And this is very important because cities are complex in space, and we need to be able to assess this spatial complexity. And also they're open source, which is also great because and you can access the source and make contributions to it. And well, I'm just gonna leave the link here for their user guide, but it describes pretty much what we're gonna go through now very quickly. So the model is based on the cooling capacity of urban green infrastructure, which they took from this paper. And basically you compute for each pixel. So this sub I in the formula refers to each pixel. For each pixel, you compute a cooling capacity index, which is weighted sum of the shade, which is this S, so the shade that trees provide, the albedo, that it's basically the fraction of radiation that the materials absorb. So as we know, artificial surfaces tend to absorb more radiation, and then they often release it in the night, which is why nights are way warmer in cities. And at the end, the evapotranspiration, which is the plants transform, they modify this water balance with their evapotranspiration process, which also affects their temperature. So these are the three factors that count to the cooling capacity. And additionally, many studies had observed that large green areas have a cooling effect. So even if you live next to a big park, but not in the park itself, you might be exposed to lower temperatures just thanks to this large park that you have close to your home. So they added this factor that for these green areas around a neighborhood, around green areas, we can observe lower temperatures, so it has larger cooling capacity. So once we have computed these cooling capacities, we need to give the model a reference temperature and urban heat island magnitude. So what this means is that the model does not simulate temperature. It simulates the distribution of temperature, but we have to give him the temperature. So basically, if in a summer day, I know that here in Lausanne, in the surroundings, the rural reference temperature is 20 degrees, and that in the city center, it's 25. So I know that there's these 5 degrees of urban heat island, and I give the model these two parameters, the reference temperature and the urban heat island, and the model is going to try to estimate how we distribute the temperature across the whole city. That's the way it works. So it does it with this formula, and this HM, it's the heat mitigation index, and it's basically a shorthand to say the heat mitigation index is the cooling capacity of the pixel, or if it's a green area, this modified with extra cooling capacity, just a shorthand for that. So basically, the pixels that have most heat mitigation will have the lowest temperature, and the pixels that have least heat mitigation will have the highest temperature. And at the end, after all this, they just use a convolution to spatially average temperatures, because the change, like you cannot have a pixel at 30 degrees and the next pixel like 10 meters away at 20 degrees. That would probably be wrong. So this is why we use spatial averaging with a radius that we can calibrate. So this is their model. This is pretty much what the user guide says, and here's the recipe that we designed to use it. So we need 4 main data inputs. The first of all is a land cover raster. This is very simple to get. We can get it from remote sensing data or from governmental open data sites. In our case, we took the official survey of the Canton of Vaud, which is where Lausanne is. And it's a vector dataset that we rasterize at 10-meter resolution. So we have a 10-meter map of land use land cover for Lausanne, but you could get it in almost any city in the world. Then we need a biophysical table. So for each land use land cover class, like it could be a building, a park, sidewalk, a road, a garden, and so on, we need to have a crop coefficient code, which is you can find them in the literature for cities. So like they reflect how plants, they reflect the evapotranspiration process of plants. So they're gonna land use codes with vegetation, like parks or green areas, are gonna have different crop coefficients that buildings or park, but you can find them in the literature. Albedo coefficient, so this fraction of absorbed solar radiation. Again, you can find references in the literature, you're going to see that more artificial surfaces are going to have are going to absorb more heat. And finally, shade coefficients, which is the fraction of the proportion of tree cover that each pixel of the class has. In our case, we took aerial imagery and we extracted the trees at 1 meter resolution, and we coupled the 10 meter land use land cover map with the 1 meter tree map, and we estimated for each land use class, like buildings, parks, and on average, how much of the pixels were covered by trees. So I'm gonna leave you a reference of the paper on how we did it later, so you can see it with more detail. And the third ingredient that we need is a reference of evapotranspiration raster, which we can estimate for air temperature. And there are different formulas, and there's a Python package called PyETO that you can use to estimate that, and it's open source. And in our case, we use the MetaSwiss data, temperature data, to estimate this evapotranspiration. And finally, we need an air temperature data for the days that we want to simulate urban heat islands. So I put together all the stations that I could find open data for, and this is the Lausanne study area, and this shows the different stations from different sources that I'm using in this study. So once we have all this, we calibrate our model, and this is what we do in the paper that's in this link that I'm gonna show at the end. We have the calibration has been set up as an optimization problem where we want to find the parameters of the urban cooling model, the weight of the shade, the weight of the albedo, the weight of the evapotranspiration, the distance in which green areas have cooling effect, and the mixing radius. So we find a combination of these parameters that minimize the error between the air temperature stations data and the maps that we simulate. And we solve it with a simulated annealing procedure. And we have also created a Python package to calibrate the model, which also even has a command line interface. So if you have the ingredients, you can use this package and it will calibrate your model automatically. So regarding the performance, we compared it with a linear regression with remote sensing data. So we did a regression with satellite land surface temperature. This NDWI is the vegetation index and the elevation. So we did a linear regression with this and compared it with the INVEST urban cooling model. So the INVEST urban cooling model outperformed this linear regression in the three metrics. So the R squared, it's 0.9, whereas the linear regression is 0.83. The mean absolute error is of 0.95 degrees Celsius and the root mean square error of 1.14. And well, I said we compared it like these metrics, we compute them out of 8 dates for which you could find good satellite images in the summers of 2018 and 2019. And these refer to 9 p.m., so it's nighttime temperatures, because there's almost no daily heat island in Switzerland. Maybe there's a 0.5 degree difference, whereas at night the difference can be about 4 degrees or 5 degrees. And I say linear regression because we compared it, we did cross validation to select the linear regression because it performed more robustly than the random forest or SVM regressor. But regardless of all these, the urban cooling model performs even better. So, but besides the statistical determination, we have two key advantages of the urban cooling model. The first one is that we can relate the parameters of our model. So these weights of evapotranspiration, shade, albedo, air mixing radius, and distance of cooling of the green areas. We can relate them to physical processes Whereas if we were using a random forest or an SVM, the parameters of the model are really hard to map to these physical processes. So they're harder to interpret. And again, another huge advantage is that once we calibrate it, we can use this model to evaluate like synthetic scenarios. So basically from master plans or urbanization prospects. So if they told me they're going to build a bunch of residential and business buildings in this green area, I can use my calibrated model to try to estimate how much hotter that new area is going to be after we build these buildings. Whereas in the regression from satellite data, I don't have satellite data for this synthetic scenario because it doesn't exist. So I could not do that. This is why this is another major advantage of how we can use the urban cooling model for planning. There are two main limitations that I need to note. The first is that our ground truth data is quite sparse in space. You saw the map before. There's 11 stations, and the extent of Lausanne is of 100 square kilometers. So it's quite sparse. And there might be other sources of data or mobile sensor networks. And the calibration procedure would be the same. It just would be more precise in space if we could add these more fine scale temperature measurements. I would like to find a way to work with that. And another major limitation is that the air mixing and the cooling effects of green spaces are not homogeneous in space. So we do this Gaussian convolution, which is homogeneous in space. But we know from MetaSwiss itself that the air mixing is not homogeneous and makes sense. So in some papers of MetaSwiss, they describe more the several meteorological phenomena here in Switzerland that could help us make a more realistic mixing of air. But this is our first paper on that, so we're still just using the urban cooling model as it is. But I believe this non-homogeneous air mixing should be incorporated in the model because it makes it more realistic. And I'm just at the end, I'm just gonna illustrate now how we're using the model for planning, because what I've explained you so far, it's the paper that we have submitted recently on how to calibrate and evaluate the model. And now we're working on a paper on how we use it for planning. So we want to see the effects of the spatial pattern. So the amount of trees and how we distribute them in space. And we want to see the effect of that on urban heat mitigation. So we have set up the experiment as follows. So we take this 10-meter land use land cover raster and the 1-meter tree canopy raster, and we refine our land use land cover codes. So our building, sidewalk, parts, and so on. We reclassified it into a bunch of subclasses according to their proportion of tree cover. So a pixel of sidewalk could become a sidewalk with a low tree cover, sidewalk with medium tree cover, and sidewalk with high tree cover. We do that because if we want to simulate land use change and building, I don't know, if they're gonna build a new neighborhood and so on, if I had to draw like a land use map with 1 meter, with trees at 1 meter precision and so on, it would be very hard. It's instead way easier to just change a 10-meter pixel from, if we say we're planting a tree here, we're gonna change this pixel from a sidewalk with low tree cover to a sidewalk with high tree cover. And so yeah, this is what I just explained. We mimic these planting trees by upgrading low tree cover classes to its corresponding high tree cover class. And we have mapped the pixels where we can do that. So we exclude all the pixels that are taken by buildings or roads where we cannot plant trees even if we would like to. So we take this reference data from the 9th of August of 2019. We took this data because it's the data with the highest observed heat island magnitude of almost 4.5 degrees Celsius at 9 p.m. at night. So the rural temperature was 20 degrees, but might not seem much, but it's 20 degrees Celsius at night. And this is the rural one, so it means that in the city center it was 4.5 degrees more, so 24.5 degrees, which for a Swiss city, it's a very hot nighttime temperature. So now we want to see the effect of the proportion of tree cover. We use our calibrated model and we ask this question. So how many pixels can we convert to a high tree pixels, and how much heat would that mitigate? So I generated this set of synthetic scenarios where you can see in the columns we increase the proportion of pixels that we change to pixels with high amount of trees. So in the first row we don't change any pixels, so that's the land use land cover as we have it now. And in the last row, we change all the pixels that we can to high tree pixels. So we can see that in the first row is the land use land cover. The second row is the simulated nighttime temperature. So we see that we have these temperatures that get to 24 when we don't change anything in the left. In the city center, the temperatures get up to 24. But as we increase the proportion of pixels that we change to pixels with high tree cover, this heat island can be really mitigated. And the bottom row shows actually the difference between the temperature that we observe when we do not change anything and the temperature that we simulate when we change trees. And at the end, if you go at the right, when we change all the pixels, we could see more than 2 degrees mitigation. So people in the city center would be exposed to, like, instead of these 24 degrees, it would be around 22 degrees. And this is what the sort of experiments that we want to do with our model. And this is why we say it's a valuable asset to use for planning. And so now we've just checked the effect of the proportion of tree cover. So just planting trees, because we know planting more trees, we're gonna get lower temperatures. And I forgot to mention, these are the pixels that we convert are chosen randomly here. But here we did another experiment where we said, let us now try to plant trees. So to upgrade these pixels in 2 different ways. One in which we prioritize scattering trees, which increases the shade, because if we have a large forest and then we have all the buildings and sidewalks, we're gonna have less shade in these buildings and sidewalks than if we had a bunch of trees for the same amount of trees, but a bunch of trees scattered around, we would have a more shade efficiency. But the other approach would be to do the opposite, prioritize clustering the trees, which in this case increases the evapotranspiration and the large green area cooling. And this is the results that this is the plot that I'm working for the new paper. And we see that when we scatter the trees at the very left, this proportion of landscape, it's the proportion of landscape that's occupied by high tree pixels. So when we increase the proportion of landscape and decrease the temperature, if we use this scatter strategy, so we scatter the trees, we get slightly lower temperatures. And then the other three plots show different the relationship with different landscape metrics of this temperature in 2 scenarios. So this is something that we're working now, and we'd like to publish it soon. And I would also like to add to not only see the effect on the temperature, but how many people lives in every pixel. So how many people would be exposed to less temperature? Because if we mitigate heat where not a lot of people lives, it's maybe not so valuable as mitigating heat downtown. So this is another plot that I would like to have soon. And well, we have a manuscript under preparation that hopefully should be by next month, submitted by next month, so a preprint will be available. And that would be it. I just leave a bunch of links here. So this is the link to this slide, so you can click all the links that the slides include. Our preprint of the paper of the calibration and evaluation of the performance of the model, GitHub repositories with the library to calibrate and the materials that we have used so that you can reproduce our results. And well, here are the references, but if you just go to the link to the slides, everything is there. And that would be it.
Okay, thank you, Marty, very much for this interesting talk. And I'm just checking here in Q&A if we have any questions from our audience. And it seems like we do have. Philip is asking, very interesting to see urban heat islands mitigation quantified. Is City of Lausanne using your group's findings to justify planting more trees?
Well, not yet, because this preprint, we submitted it in July, and we're working on this other paper now. But I had a master student that did his master thesis on this topic with me, and we worked with a guy in the Parks and Forest Services of Lausanne, and he was really interested in this project, and he helped us. So he helped us when we say these are scenarios of planting trees by upgrading pixels. He helped us designing that, and he works in the Parks and Forest Department of Lausanne, and he's really interested to have into having these results to like tell his superiors, like, we should plant trees, look at this report, what we can get out of them. And also this master student that we had that finished his master, he's going to be working on that in Geneva, because one of the external experts that was in his thesis defense works in an urban heat island mitigation project in Geneva. So now he's going to be working there. I don't know if they're going to be using this model, but probably yes, because that's what he did in his master thesis, and that's what Geneva, the guy in Geneva was so interested in.
Okay, seems like we have a few more questions, and I think first there is a follow-up question from Philip, and he's asking whether this model works also outside of the study area, for example, in Lagos. Or is it only applicable to Lausanne?
No. I mean, so the thing is, if you go to the GitHub repositories, it should be quite easy to see how you could apply the model anywhere. It's just that when you calibrate, it's probably going to give you different results. So for instance, an interesting result is that here in Lausanne, we see that scattering trees, it's probably more efficient than just clustering together. And I saw a study that compared Baltimore and Sacramento that said that in Sacramento, it's more efficient to cluster trees. And in Baltimore, which has a climate that's more similar to Lausanne, it's more humid, it's also more efficient to scatter trees, just like in Lausanne. They say that it's probably because in Lausanne and Baltimore, in humid climates, you don't need to help the evapotranspiration so much by like planting them together, but it's more efficient to just scatter them because you need the shade. The shade is what's going to cool. But in Sacramento, which is way drier, it was important to cluster the trees so that they could be efficient in evapotranspiration. So my point is, yes, you can use the model pretty much anywhere. The calibrated coefficients will be different, but that's kind of the beauty of it, because you can then interpret your parameters with the local climatic conditions of your study area.
Okay, and one last question before we go to coffee break. Terence wants to know, how do you assume a specific combination of parameters for your optimization process? for example, crop, albedo, shade, etc.? And how do you know whether one combination of parameters is better than the other?
Yeah. So the parameters are like given in the model, are the parameters of the model. There are some other parameters but these are the main parameters, and there's actually a paper that does a sensitivity analysis. But the model, that's how the model is done. So these are the 5 parameters, and these are the parameters that I chose to optimize. Some have larger effects than others, but we explored the effects of all of them. And we use a simulated annealing procedure in which we simulate maps, we see if the maps match the air temperature stations, and we compute a metric, the R squared, or the mean absolute error. And basically, this is how we know if one combination of parameters is better than the other. So we use this simulated annealing procedure to test very different combinations of parameters, and then at the end we select the combination of parameters that gave us the best result.
Okay.
It's a heuristic, so it's not exact optimization, but it's you cannot optimize it otherwise. I mean, it has to be a heuristic because the model can be very complex in space.
Okay, thank you, Marty, and thank you all for your questions. And I would suggest that maybe you use your coffee time and think about and ask other questions to Marty in Discord channel. And with this, I will conclude our first 2 talks in this room for this day, and we will see each other at 10:30 with another talk after the coffee break.
Thank you, Matus.
Thank you.
Hello there.
Hello.
Are you able to hear me?
Yeah, perfect.
So welcome everybody. Today I'm going to introduce Fernando Mendes. I'm Antonio Ercole de Luca. Good morning. And he's gonna tell us about TeslaKit, an open source Python-based library for coastal risk assessment in a changing climate. Fernando Mendes, correct me if I'm wrong, do you work for University of
Cantabria.
Cantabria, exacto. Bien, I let you speak, so see you for question answering.
Thank you. Thank you, Antonio. So let's share this. Okay, so thank you, Antonio. Thank you for the opportunity of being in this virtual conference. So I'm going to present the results of a project that has involved a lot of researchers from different organizations like Oregon State University, University of Auckland, NOAA, and ourselves, University of Cantabria. So what I'm going to present is the results of a 4-year project funded by the Department of Defense of United States. So what is the purpose? So what is the research goal? So the research goal is for these 4 particular locations that are military installations in the Pacific Basin. The objective is to create emulators to explore hypothetical flooding events that has not been observed in the historical record, but are plausible. So with this in mind, so let's zoom a little bit in the areas of study. So we are going to study the military base in San Diego. In San Diego, we are going to analyze also the military base in Kaneohe, in the island of Oahu, in Hawaii, and also 2 military installations in the atoll of Kwajalein, and the military installation that is in Guam. So let's focus. What is the problem? The problem is our objective is to obtain flooding levels, and in order to do that, we use a proxy, a metric that is what we name total water level, TWL. That is a summation of different contributors, such as the mean sea level, the astronomical tide, the non-tidal residual, that is all related with to mean sea level anomalies or storm surge component, and also the wave run-up that depends on the slope of the beach and of the characteristics of the wave height and the wavelength or the wave period. So as you can see, this problem is multivariate. So let's see what kind of data we have for addressing this problem. And I'm going to put just the example of San Diego case. So here in the upper part is where is located the Coronado military base. So what we want is to obtain the extreme value distribution of total water levels in order to be able of knowing how often this area is flooded, in order to obtain damage and in order to characterize risk, not just for present climate, but also for a changing climate. So which kind of data do we have? So here there is a tidal gauge in San Diego, and this tidal gauge, we are very lucky in this case because the time series starts at the beginning of the 20th century. So we have more than 100 years of the sea level, and the sea level is composed by the astronomical tide, the storm surge, and the monthly mean sea level. So these are the 3 components that can be seen in a tidal gauge. But there are other other components, as I explained previously, that are the components that are going to flood from the open ocean. We usually characterize this in terms of the wave height, the wave period, but here we see that the time series of the waves, the wave height and the wave period, starts 40 years ago. So we see the part of the variables that is contemporaneous, we see that in order to obtain total water level, we have 40 years of data. So what is the usual procedure? The usual procedure is to pick up for instance, the annual maxima of the total water level. And once we have this annual maxima, we apply standard. We can apply standard extreme value and a standard extreme value model, and we can obtain and we can extrapolate for a particular, for instance, for 200-year return period or whatever. What is the problem? The problem is that the amount of data that we are using here is so small. We are using just 40 years, 40 data, that the confidence intervals for large return periods are huge. So these trumpets are huge. So the objective is to diminish the size of these trumpets. So what else? What we can see is that the larger events are associated with different combinations of the variables that are defining the problem, like the tide, the non-limit sea level, the surge, seasonal effects, or the wave run-up. So the problem is multivariate. So let's try to analyze the problem taking into account the different components. So we have different components. We have waves, we have wind direction, wind speed, pressure is also affecting, sea level anomalies, river discharge, astronomical tide. So the problem is very multivariate. So what's the problem? The problem is that if we have a lot of variables, we need to obtain the joint probability distribution of all these variables. Besides, if we are addressing a problem of climate variability or climate change, it would be great to define some climate drivers that drives all the variables that are defining a particular event. So what is from the point of view of the objective is, okay, so we want to obtain flooding levels in the area of study, and for that we are going to use a hydrodynamic model, and we would like to know for each variable of wave height, wave period, wave direction, etc., which atmospheric pattern is responsible of that. And every day we are going to have a different pattern. These are the patterns that we model at daily scale, but these patterns are also affected by other scales, like seasonality, like intraseasonal variability, or like ENSO, El Niño variability, that in the Pacific, the interannual variability is huge. So let's go now to the patterns at daily scale. So if we pick up the daily sea level pressure fields from an atmospheric reanalysis, and we have 40 years of data, and we say, okay, let's reduce the dimensions of the problem. So we apply principal component analysis, we obtain the EO waves. This is the first, the second, the third EO wave, and these are the PC1, PC2, and PC3. So, and other, like the first 50 modes. So if we want to summarize all the information of the daily sea level pressure fields that are going to drive our waves, or our sea level, one thing that we can do is, okay, let's play with PC1, PC2, and PC3. So we can define a space of 3 dimensions. 3 dimensions is nice because in our, we can represent easily. So these are all the daily events in terms of pressure, and the objective is to obtain clusters. And for that, we are using different methods, self-organizing maps, or in the particular application in this project, we are using K-means. So what does it mean? If we go specifically to one small cluster, this is what we obtain. So the light blue dots are the points that belong to the large white dot that represents one cluster. So after playing games with different combination of clusters, in this project, we are using 36 patterns. And these are the patterns that define the, let's say, the climate of driver that affect the waves and the storm surge at our study area in this case, in San Diego. So next step is to attribute to each particular cluster, for instance, to that particular pattern, which are the waves that belongs to that cluster. And for that, we are going to obtain the joint distribution of wave height, wave period, wave direction, storm surge levels, and all the variables that are involved in our problem. So let's say that our problem is a problem of joint probability distributions conditioned to a particular part of the climate. In this case, daily weather types. So this is what we have for one pattern, but we can do this for all the 36. We have wave height, wave period, wave direction, or storm surge levels. So once we fit these two, in this case, the wave height and the wave periods are fitted to a generalized extreme value distribution. The storm surge is fitted to a waveful distribution. For the wave direction, we are applying a kernel model. So once we have this, let's explore the climate variability. So we have the patterns. We have these 36 patterns, and these patterns, it's clear that we are not going to have the same patterns in winter or in summer. So just plot the occurrence probability. And we have here summer. The darker the color, the larger the probability of occurrence. So for instance, where I have the pointer here in summer, this pattern that is located here is very often. But these patterns over here are practically impossible in summer. These patterns affect in winter. Okay, so we have a clear division between the patterns in summer and the patterns in winter. So we are modeling the seasonality just by attributing for this categorical variable the occurrence probability in summer or winter. Okay, so this is for the summer, this is for the winter. Okay, so if we go back here to our calendar, Wednesday, Tuesday, Monday, Sunday, we are modeling the seasonality, but there are other time scales that are of interest. Let's go to the scale at an annual scale, because this is going to give us the information of El Niño. So I'm not going to explain this in detail because a colleague of mine, Sara Ortega, in 1 hour from now she's going to explain this very well. But based on sea surface temperature fields, we are able of obtaining, using the same methodology, the same approach, patterns that represents typical years in the Pacific Ocean in terms of sea surface temperature, like El Niño year, La Niña year, or transition years. Why this is so important? Because when we project the occurrence probabilities of the daily weather types to each particular annual weather type, what we see is that there is a clear distance signal depending on the year in which we are. So patterns here to the left are more often during El Niño year. Patterns here to the right are more often during La Niña years. And this is very relevant if we want to build an emulator, a climate emulator, taking into account the chronology at different time scales. The other time scale that is pretty relevant is the scale of intraseasonal scale. So we are modeling the effect of the Madden-Julian oscillation that in rough terms is, let's think in a huge cloud that moves eastward throughout the equator and with a periodicity between 50 to 80 days. So based on that, we can represent our marvelous maps of red colors that define the occurrence probability, and we can see that depending on the phase of where this convective cloud is located, we have a different signal in terms of the occurrence probability. So we are modeling intra-seasonal variability, seasonal variability, the annual scale. So the point is, now we need a machine that is able of creating chronologies, taking into account these scales. And for that, we are using a chronology model that is a climate-based autoregressive logistic model that give us the information of once we develop this emulator. So the model is able of giving the categories of weather type 7, 7, 6, 5, 5, 4, and so on, taking into account the scales of interest, or at the scale of intra-seasonal, seasonal, and annual weather types. So once we have this, let's validate this. So on the right-hand side, here you see the historical probability of occurrence. What we are representing is the occurrence probability throughout the year that starts here, in our case, in June, until the 31st of May. And the color represents the occurrence probability. And here you see 36 colors, 42 colors, including also tropical cyclones, that define that if these colors define our problem in terms of the category. So once we simulate one simulation, this is the results of the synthetic simulation, another simulation, another simulation. So if we perform this thousands of times, what we obtain is this map of simulation of occurrence probabilities, in which we can see the clear signal of seasonal cycle, that there is a specific area in which, for instance, these gray colors that are the area of the year in which we can have tropical cyclones and so on. So, okay, so we have the model. Let's apply the model. So this was our starting point, that we were using these 100 years of sea level of astronomical tide, storm surge, and mode limit sea level anomaly. But from the OpenSea, we have the wave height, the wave period, and we were able of building the total water levels. So with our model, we are able of attributing which are the annual weather type or the daily weather type at daily scale. So let's focus a little bit on physics, on the climate variability. So in 1983, in San Diego, in the Pacific Basin, there was a huge El Nino. So this event is represented here by this annual weather type, ref. The storm surge in this particular year were larger. The waves were larger. So the response, the total water level response in year 1983, are the larger total water levels throughout the records. So for that, it's very, very relevant to couple of all the variables and the driver that define all these local variables. Okay, but we have the machine, and the machine is able of creating synthetic records. And in this case, I'm representing 10 years of records. And in these 10 years of records, we are able of seeing neap tides, spring tides, the mode limit sea level variability. We can see the winter and summer of different years in terms of the wave height and the wave period. And this is the response of the total water level. And this is when we run the model 10 years, but we can run the model 100 years or 500 years. And what we see here is that once we have this emulator, we are able of creating plausible synthetic events that has never happened in the past, but has an occurrence probability of being able. Okay, so we have the model. Next thing is, okay, let's focus, for instance, in the annual maxima. And this is what we are representing here in the lower panel, the lower plot, with red dots. Red dots are the annual maxima. So one question that we would like to address is, okay, for our patterns, let's calculate when an extreme event occurs in a specific pattern. So here we see on the right-hand side, the map of occurrence probability of the annual maxima. And we can see here that this cluster, and this cluster that corresponds to this load system creating huge waves that arrive to San Diego, or this event, huge waves with huge wind that is going to drive and is going to increase the water level, are the patterns that are more, let's say, dangerous. And with this specific model, we are able of modeling this time scale. Another way of watching the results is, okay, let's represent the particular combinations of events that define the maxima. And this is pretty relevant. And this is when all these Jupyter notebooks that I'm going to present in a couple of minutes are totally relevant, because we can track all the results of the model in a nice way. Okay, so this model has been published recently, last year, in JGR Oceans. So probably you have noticed that the aesthetics of the plots that I have showed you are not Python aesthetics, but MATLAB aesthetics. So when we started to do this project, we said in terms, we created an analogy in terms of creating a machine. And the analogy was, let's create a bike. And during the first year, this is what we built. Just mixing some of the pieces, we created a bike. But we wanted to create something more powerful. Let's say that at the mid of the project, 2 years from the beginning, let's say that we created this car. So we realized during the first year that it was better to play not just with MATLAB, but starting to play with Python. And now I would say that 98% of the codes are in Python. What is relevant also is that we are following this Jupyter environment for showing and for running all the models. So instead of creating a car, I would say that we have created another kind of device, like the Millennium Falcon. What is the nice thing of creating this Millennium Falcon? The nice thing is that it's built of many pieces, many building blocks. And what is the advantage of creating these building blocks? Is that if we sort the building blocks in different way, we can create different machines. From the point of view of coding, thinking in building blocks is better because it allows to create a more, let's say, strong, power, a robust machine. So, and this is when I move slightly to the GitHub page. So it's TeslaKit in GitHub. And this is what you can see in the web page. This is the project map. And just as an example, what I'm zooming here is the representation of downloading the Madden-Julian oscillation for a public website. Once we have the Madden-Julian oscillation, I play games and I apply some algorithms and I obtain some categories. And all of this is displayed in these Jupyter notebooks, in which it's easy to follow what I'm running and what are the outputs. And for instance, on the left-hand side is when we download the data, when we apply the clusters, and on the right-hand side is when we apply an autoregressive logistic model. And this panel of colors represents the p-value of the autoregressive logistic model. So nice thing of this is, okay, we are creating TeslaKit, that is the machine, but it's built with blocks, with building blocks. But the point is that there are many building blocks that we could use in different way. If we are, let's say, if we try to order all the building blocks, what we can do is we can create libraries that can be very useful for our coastal engineering community. Building blocks, libraries for data management, job management, machine learning. I have showed you some examples of machine learning tools that we are using, but also libraries for multivariate extremes, Monte Carlo simulations, etc. So in this way, I would say that we are going to be able, this is our next objective in the following projects, to define a collection of libraries for helping to solve problems that are very common for coastal engineers and coastal scientists. And I think that's all. So thank you very much for your attention, and I think I have finished.
Thank you very much, Fernando. So now that we have at least 3 minutes, maybe 4, I would say let's start with question answering. So everyone has a question, can do it now. So, well, in the meanwhile, I have a question, maybe 2. The first question is, how did you choose the number of clusters in the clustering algorithm? You follow a certain, let's say, algorithm, or?
So there are, let's say, automatic algorithms that helps you to select the optimal number of clusters, and we have tried several of them. But at the end, what you have to consider is you need a compromise between how well you want to represent the climate of patterns of sea level pressure fields and how many data you are going to have to fit each cluster. So these 36 clusters is something in which we have, in average, like about 200 of events, of daily events, of waves, that are the minimum amount needed for fitting a joint probability distribution.
Okay.
And on the other side, from a climatic point of view, you have seen that these patterns are able of reproducing the seasonal cycle, interannual variability in a nice way.
Okay, thank you. So there's a question from Michael Turner. Perhaps I missed it, but how did you add future climate drivers into the model?
Yeah.
For instance, increasing mean sea levels?
Yeah, so mean sea level, so if you remember the equation of total water level, at the end, the equation of total water level is a summation, a linear summation of terms. And one of the terms that I haven't focused in this presentation is how mean sea level is changing. So sea level rise can be added easily to the model, to the total water level model. This is if we want to introduce sea level rise. If we want to introduce changes, for instance, in the occurrence probability of, let's say, of the climate of pressure patterns. So we have to go to some climate change scenario, for instance, the RCP 8.5 for a particular time slice in the future. There are like 20 climate models, CMIP5, CNIP6, that is the new generation. And you can download these climate models and you can see how are the occurrence probability of these daily patterns in the future. So just by changing these patterns of pressure, automatically you can obtain the response in the climate emulator. This is, let's say that this is the basic idea of statistical downscaling.
Okay, I think we're good for today. Thank you, Fernando. And I would pass to the next speaker.
Thank you.
So, bye. Which is Lucas van der Meer from University of Salzburg, Department of Geoinformatics, which is talking about Python machine learning. Oh, sorry.
Does this work? Sorry.
Yeah. So a semantic query system for Earth observatory imagery. So I give you the speak.
Thank you. Thank you. So yes, let's start with this slide. I'm going to talk about the semantic querying system for Earth observation imagery. And like over the past years, in the past 10 years, let's say, there we got a lot more Earth observation data. Yeah, there are a lot of satellites out there in space that take pictures of the Earth on a very regular basis. Yeah, and to get an idea of how much this is, if we only look at the European satellite data program, then this is already 12 terabytes of data every day. Yeah? And in 5 days, there is a full global coverage of satellite images. And of course, that's great because these data, they can be very useful to a lot of fields. I think you can all imagine if we look at our Earth at a very regular basis all the time, again and again, we get a large amount of data that we can use to in a lot of application fields. And in the Copernicus website, they also mentioned they're very proud of that, and it's also very good. Yeah, that all this data, this 12 terabytes of data every day, yeah, they are available and accessible to any citizen and any organization on the whole world, yeah, for free. Yeah, so anyone in the world can get these data. Yeah, but what then we ask ourselves is, of course, a very good start that you can get this data, but what about usable? Yeah, so can also any citizen and any organization in the world really make use of this data? And that answer is, of course, still no, because we see this very nice satellite image, yeah? But what this data really is, what the computer sees, is only a lot of numbers. Yeah? And to interpret these numbers and to extract information out of this image, that requires a lot of expert knowledge, programming skills. Yeah? And these expert knowledge and programming skills, one, it's scarce, not everyone has that, and it's expensive also, of course. And that is something that really limits the potential that this satellite data has. Yeah, there is a lot of data, anyone can get this data, but you still need a lot of expert knowledge to actually make use of this data. Yeah, and then that is basically the thought that brings us to the project I'm going to talk about. Yeah, can we not enable this information extraction from satellite images without the need for very advanced domain knowledge and without the need for programming skills? And that is what we then call semantic querying, yeah, which basically means to exploit the power of the satellite imagery and to get answers to questions that you express in real world terminology, and that the complexity of all this data processing that is going on in the back is actually hidden for the end user, which will enable the end user to ask questions that it wouldn't, in like words that you would normally ask a question to a person, but instead you ask it to your database and it gives you an answer. Just to give an example of more practical example of what we basically mean with that. If I go to Google and I ask Google how many people live in Basel, then it gives me the answer. Yeah, this is a question expressed in words that I would also use to ask a question to a person. Yeah, I now ask it to a database. I don't know anything about population data. I don't know where they get this data from. And also I don't have to write any line of SQL code. Yeah, I just ask the question in normal words and Google gives me the answer. And then I think, can we not also create such systems for satellite data and ask questions in the sense of, for example, which municipalities in California were most affected by the wildfires in summer 2020? Yeah, or how many square kilometers of the Amazon rainforest were deforested in 2019? Or to get it a bit closer to home, at least for me, what percentage of Vienna's area was green space in the summer of 2020? Yeah, all these kind of questions, the answer might very well lie in satellite data, but to get the answer to these questions, right now you need to know how to process satellite data, how to analyze it, and you need to have quite advanced programming skills to actually get the answers to these questions from that large amount of data that there is, and that is all free. Yeah. Before we get too happy, I will directly say that we are definitely not yet at this point where we can simply ask such a question and our system will say, oh yeah, that's this and this and this. Yeah, because this is not as easy as it might maybe look like, but we are starting, we're really at the starting point of creating a system that at least hides some of the data analysis complexity to the end user, and to some extent can enable users to express their questions in real world language. And it's that system, at least at the point where we are now. As said, we're really at a starting point, but that I will present today. So the system overview looks like this, and I will explain a bit what you see here. Yeah, so we have here at the right, we have the domain experts, the people that really know what's going on with satellite data. Well, at the left side, we have the end user that does not know that, but that does want to get information out of this data because it can use this information for his or her work. So the key point here is that the data, so the source data, the satellite images, they are in this fact base, yeah, and they are, they are separated from the knowledge base, where the experts bring in their knowledge, where that knowledge is stored. Then the user does not know anything about what's going on here. The user asks a question, like formulates a semantic query, and that interacts with this inference engine. And this inference engine then says, okay, this is what the user asked, and the inference engine translates between the knowledge base, so the knowledge that the expert bring in, and the raw data that we get from the satellite. It now all looks very abstract, but later on we will see better how this works. And I put this Python logos here because in the end we are at a Python conference, and both the inference engine, yeah, this is a Python package in our system, and it's built on top of the Xarray package, which some of you might know, for spatial temporal raster arrays, which we also will look into later. And the fact base, yeah, so how this data is stored, is also accessible for the inference engine through a Python API, because we use the Open Data Cube infrastructure, which is a way to store your data and be able to do very efficient queries in your data over space and time. Yeah, so that's this part. The fact base is what I will go into first, because in our system it's not just the raw satellite data that is stored there, but we already put in some extra layers that will help our system later on to analyze the queries that are expressed in real world language. So our data storage, again, in an abstract figure, looks like this. So this data cube, yeah, that looks like this, which has spatial dimensions and a temporal dimension, and you can query such a cube over space and time. So you define an area of interest and you define a time span that you're interested in, and then this open data cube system, yeah, which is accessible through a Python API, can then very efficiently retrieve the data that's in the cube for you. But besides the normal satellite image, yeah, which here is called satellite image, we have already some extra data layers in there, which are completely automatically generated. And these layers already give, to some extent, an interpretation of what we see in the raw satellite data. Yeah, it cannot completely say, okay, this is a forest, this is a lake, this is a road, but it gives to some extent, yeah, based on the color composition of these satellite images, it gives some interpretation of what we see there, and I can show you how that looks. So that's here. Yeah, so this is what we call in our system, we call that semantic enrichment. So the raw data, the pure raw data, we already enrich it with extra layers that give an interpretation of what we see in this data. And this is a nominal layer. So it gives to each pixel, defines this pixel belongs to class number 1, this pixel belongs to class number 10. And these classes, they look like this. So they basically say, this pixel is strong vegetation with a high near infrared, yeah? Or it's a weak vegetation, or it's either bright barren land or buildup. And there you see that this is only an interpretation to some extent, because we cannot in an automatic way see on a satellite image the difference between barren land or buildup. And the same is, for example, with water. Yeah, we cannot see the difference between shallow water or shadow. So this first step also doesn't try to do that. It does as much as it can in an automated way, and we store that interpretation as an extra layer in our data cube. So then let's go back to my slides. Sorry about that. So I will go on here. This maybe works better. Yeah, so there are some extra layers also that gives an index on how green each pixel is and on how bright each pixel is. And there's also an extra haze mask. Yeah, so these are all extra data that can be generated fully automatic. So parameter free, and it can be generated for each satellite image. So we don't have any work with that. This is a fully automated process that creates this extra layers for every image that is in the data. Yeah? And then this image that I already showed, this image here, then in this nominal interpretation looks like this. Yeah, so for each pixel, for this one it says, oh, probably this is vegetation, probably this is water, this is either barren land or buildup. That is the starting point for our data cube. Yeah, so where we store our data. Then I'm going to go to the user interface. Yeah. So the user doesn't see anything of what's going on there in the back. So I will show show you the demo of our system. So our system, our demo server has now, for at least for now, only Sentinel-2 data, Sentinel-2 images for the whole country of Austria. That is the demo data that we work with. The system is not necessarily limited to only Sentinel-2 data, because this automatic enrichment of the data also works for example, Landsat data and for other sources. But for now, in our demo service, we limited ourselves to Sentinel-2 data for Austria. So when you come into this demo as a user, the first thing that you would do is to select a spatial subset for your query. Yeah, so you could select here polygon. Yeah, and at the same time, you also select a temporal subset. So you're completely free. Sorry, I should not go to 21. Completely free to choose in which area of interest and which time span of interest you want your question to be answered. Then the query will be expressed without any need for programming skills inside a query model. And here we already have some pre-built models. So how this looks, I will choose one of these. So let's say again, sorry, I will go to this one. So as said, the part where an expert brings in knowledge is clearly separated from the part where you then use this expert knowledge to express your query in real world language. Yeah, so the only thing that you basically have to do is to import predefined entities. Yeah, and these predefined entities, so this first part, this is what refers to this knowledge base. Yeah, so this is where expert knowledge is brought in. But because of our extra data layers that we have, this is already made a lot easier even for experts than when you only have the raw data. So here we say, here the expert says, okay, water, we define something as water if the pixel was put in one of these 4 categories, which come from our nominal semantically enriched layer. Yeah, so we have all the categories here that you can choose from. And we say, okay, if it's in one of these 4 categories, then we define it as water. So here we defined a real world entity water. What does that mean in terms of the underlying data? Yeah, so that is the knowledge base part where expert knowledge is brought into the system. Then the query itself can be expressed simply by connecting blocks to each other. And you don't have to know anything anymore about what data is underneath there, because we already defined what water is. So then you can use this entity water in creating your query by connecting several blocks with each other. And such a block system always starts with a defined entity, and then you can apply, and this entity you can view as a spatial temporal cube, where for each pixel it gives either true or false, meaning is this pixel water or is this pixel not water? Yeah, so this entity that was defined by the expert in the knowledge base is a Boolean data cube with dimensions over time and dimensions over space. Then when you want to get information out of there, you can apply several actions to this cube in processing chain. So you say, okay, I start with this cube, then I apply this action, then I apply this action, then I apply this action until you get to the point where you have the answer to your question. And all these blocks, yeah, what goes on in the back here, they are built on top of an Xarray function. But as you probably know, Xarray is a very large package with a lot of functions, which can be very overwhelming when you don't have any domain knowledge or any programming skills. So we, in this block system, we really made a subset of what are the core actions that you want to apply to these Boolean cubes. And each action is represented by a single block. Yeah, so here we have all the actions that you can do. There are filters, group by, invert, masks, and underneath these blocks, there is always a function that extends Xarray. But the user itself does not have to know, of course, anything about Xarray or what's going on there in the back. So I'm seeing I'm already running out of time. So just to explain what we do here, we want to count water for each point in time. So for each image that we have, we want to say, okay, how many pixels of that image were water? And we want to do that again for the next timestamp, for the next image that we have, and again for the next image that we have, and again for the next image that we have. So what we get out of there is a time series that shows us how many pixels at that time point were actually water. Yeah, and we can do the same just to show how this works. Yeah, we can name this water count over space because we always reduce our image over space to get a single value per timestamp. Yeah, we can also reduce our image over time, which gives us per point in space. It says, okay, at this location, over time, it was so many times observed as being water. I have the result of this. So normally you would save this model and apply it to your area of interest and your time span and click on start. Yeah, I already have the result of this one ready to save some time. And that one is here. So then you see what the outcome will be is a map which gives you, okay, over time, each pixel here was observed so many times as being water. And you see the river, this is the river Danube. You see it very clearly going there. And this is the time series. So for each image, it says, okay, so many pixels in that image were water. So many pixels in that image were water. Here, probably we have an image which had a lot of clouds. Yeah, because there are, of course, other things you have to think about. And you could also include that in your model to say, okay, I want to know the percentage of water, but I first mask out all observations that were labeled as being clouds. Yeah, so you can make your models more complex if you want to get a better answer to your queries. So this is a very simple example of how this would work. And then the last thing I want to do before my time runs out is to build a model that would answer one of these questions that I asked in the slides, which is how many percentage of Vienna's area is actually green space. So what we can start with is that instead of creating this area of interest by ourselves, we can use WFS layer, which comes from the open data portal of the city of Vienna. And this will draw our area of interest as being Vienna, as you see here. Yeah, so we don't have to draw this all by hand to mark what we think is Vienna, we can just import a WFS layer, and it will give us this area of interest. We will keep the same time span for now. And then I go to this model. Yeah. So first again, it shows them. Sorry, I cannot. Yeah. The knowledge-based part. Yeah. It defines the entities that we are interested in. So we say, okay, the expert knowledge that's brought in here by the expert is that we define vegetation when it is in one of all these categories of our nominal layer that we added to our data. Then we're also interested in clouds. Yeah, because we want now to mask out these clouds, and we also want to mask out snow. So we define our entity vegetation in terms of our data, our entity cloud in terms of our data, and our entity snow in terms of our data. And this is all done with expert knowledge. Yeah, and this will be stored then in the knowledge base such that other users can use this in their own models. They can use this knowledge and answer their own questions with that. Yeah, so then first what we will do is that we say, okay, we want to know for each pixel what was the percentage of vegetation over time. Yeah, so we start with our entity vegetation, because in this part, this application part, we don't have to worry anymore about what data was underneath there. It is already defined what vegetation means. And then we chain several actions to this cube. So the first thing that will happen, it will mask this with the inverse of cloud and snow. Yeah, so it will say if a pixel was either cloud or snow, yeah, we will take that out of our data. So the percentage, how many percentage was vegetation, will be based on all observations that were not cloud and not snow. So you get a better result in the end. Then we say, okay, when is it then defined as being green space? Of course, this you should bring in your own knowledge here. When do you define something as being green space? Here we just say as an example, okay, something is green space when over time, for our time range, more than 40% was defined, more than 40% of the times it was defined as being vegetation.
Lucas.
Yeah? Yes.
Cool. Shall we go to the conclusions and then question answering?
Yes, that's very good. So I need only half a minute more. Is that fine? So the last part then is that we reduce it over space and we gave, okay, how many percentage of Vienna then actually was green space? And the last thing then I show is how this result looks like. So this first layer is how many percentage of each pixel was vegetation. This is then what we say, okay, where is it more than 40% and where not? So this is basically just a true false of what was green space and not. And then I think I downloaded the result here as CSV. The final outcome is 53% of Vienna during the summer of 2020 was green space. And in that way, you see, we already get to a point where we can answer these kind of questions, not by taking away all the complexity, not by taking away all the technical knowledge, but we're already making a first step where you can answer questions with satellite data, being a user that does not have expert domain knowledge and that does not have programming skills. So yes, that was, let's go to my last slide. So if you want to get in contact about this, because I said we're only at a starting point, if you want demo access to our system, you can always contact us. We're very happy to work together and to get input on this. So that was it.
Thank you. Thank you. That's awesome. I mean, so.
Thank you. Thank you.
So we have kind of some minutes for question answering. So Anybody wants to do any question? Yeah. So, wow, amazing. Anonymous attendee. When do you think this will be at the production level?
As said, this system, as I showed it now, is already running on our own services. So if you're interested, just email me and we can give you demo access. But of course, it is still a research project, so it's not completely optimized yet for being super fast or things like this. So that will probably take some more time before we're really at that level. But everything I showed now with this block system is already running now.
Okay. So one question from my side is, did you validate the rules? I mean, okay, so the rules are done, and then the output of the rules, did you have the chance to validate them kind of manually or in another way?
This extra nominal layer, which basically says this looks like this and this looks like this, that is completely validated. That was a research project from one of our project partners, and also published a paper about that, which I of course can also share. So that is completely validated. We did not publish anything yet of validation of our system as I showed this now. Mainly also we are really at a point where we're not sure yet what we can all use this for, so what all possible applications would be. But in our project we have some users which are Austrian institutions, for example, the Austrian Climate Institution, that actually test our system and use it. And there's the goal that they will really talk back to us and say, okay, this is working good, this is not working good. So yes, that is still an ongoing thing.
Okay. So I would thank you.
Yeah, thank you. Thank you.
See you next time.
Thank you.
So here we go. So now I introduce Sarah Ortega van Vloten. Is that right?
Yes. Yes.
Okay. Which is going to talk about statistical prediction on monthly sea level. And we are starting 3 minutes late, but this is not a problem since we have a lunch break at 12. So you can take 5 minutes more. So we are going to finish 12 and 5. So up to you. Thanks.
Thank you, Antonio. Let me share my screen. Okay, as you can see it. Okay, so first of all, I would like to thank you and all the organizers for putting up this PyCon edition, which is, I think, very successful, and also for giving me the opportunity to share a little bit of my work, which is very exciting within this Python community. So here I go. My name is Sarah Ortega, and I'm a PhD student at Universidad de Cantabria in Spain, and in the ocean research. So now my presentation is going to explain an example on how to use available global data and apply machine learning into a purpose case applicability of predicting the monthly mean sea level. Okay, so my presentation is divided in 2 main blocks. Mainly, I'm going to start explaining a little bit about the motivation of the study, and then defining the model and the predictors themselves. And then I'm going to give you a quick look on the JupyterLab notebooks that I implemented. The location target of this study is located in the US West Coast, which is bathed by the Pacific Ocean.
Sarah,
and as you will see, yes?
sorry if I'm interrupting you. Maybe it would be better if you turn off your video since your voice is getting, well, noisy, okay? Because of connection. Yeah.
Okay. Wait. How do I get? Only I have to go back to. Stop. Okay. I hope you can hear me right now.
Yeah, I made it.
Yeah. Okay. So I was saying the location is within the US West Coast, which is backed by the Pacific Ocean. You will see a key driver to bear in mind. So to start off, I want to give you a sense of what is the motivation beneath this study. So on the left-hand side of you can see a figure with a differentiation of the main component of water. And aside from the wave component, that it is more relevant once you approach the coast with all the wave processes that happen, you have the sea level rise, and then the astronomical tide, which is a deterministic component due to the gravitational effect of the moon, the sun, and the earth. And then I highlighted a box here with a group of variables and processes that are accountable for the water level anomalies. And so that's what we really want to be able to predict, because anomalies can reach up to 30 to 40 centimeters. And that can be really relevant when, in terms of the negative impacts that it can have once you approach the coast. So in terms of flooding and coastal erosion and damage to infrastructures that it may produce. So if we were to have a tool that is capable of predicting these extreme anomalies, that would be great for any adaptive measures or decision making in order to decrease the risk of those areas, for instance. And you can see here an animation of the mean sea level and all the extreme are produced. So, okay. So since we are in the Pacific Ocean, we do need to understand a little bit of the processes and the timescales that are involved in order to be able to select more suitable predictors for our model. So for the larger timescale, which would be the multi-decadal and interannual, there is, first of all, the global sea level rise, easily extracted from longer records of tidal gauges. And then there's the El Niño Southern Oscillation, which is a climate pattern that is very important in the Pacific. In normal conditions, there are trade winds directed westwards around the equator, which display move sea waters that are warmer to the West Pacific, so that waters come up to the surface in the East Pacific, and there is a great temperature gradient in the equator. But as you can see here, for El Niño and La Niña would be the positive and the negative phase of this oscillation, so that those trade winds weaken down or strengthen up, and then there are anomalies of the temperature in the sea surface around the equator. So that has to be really taken into account, because with the interaction with the atmospheric system, it is really relevant. And then regarding the annual timescales, we need to consider also the seasonality that in weather patterns that can be represented by the sea level pressure fields as the ones that you can see here. And then regarding the daily scale, we're not considering that because since we're the goal is to predict monthly scale signal, that doesn't have to be considered. Okay, so to sum up, the problem can be considered complex because there are multiple variables and processes involved, aside from the ones that I mentioned, which are the most important. Possible to build a simple model in terms of just a few predictors, and that is capable to predict with a high level of confidence accuracy the monthly mean sea level in this case. So we're going to use two predictors, one for the sea surface temperature and one for the sea level pressure. Okay, so now I'm going into detail to explain the model itself. And from one side, we do have the predictor, which we have to define. We have used water level data from the NOAA, and especially for 23 tidal gauges of the US West Coast. And the process is very simple since we calculate first the sea level rise along those curves and remove it, and as well as eliminating a 3-year running average, which can be accounting for any residual signals for higher timescales. So then we would have the monthly mean sea level, as you can see here, an example for the San Diego tidal gauge. And also I've highlighted in red 3 El Niño strong years, showing that there's a high correlation between this pattern and the monthly mean sea level that we want to predict. Okay, so then as for the predictors, the first one is the regional one, and it has to do with the sea surface data that we are using also from the NOAA, and that is available since 1880 up to the present. So we have over a century of years of data, which is a lot of it. The methodology that is followed to build this predictor is included in a recently published paper by Anderson et al., which, by the way, Fernando Mendez has been explained in full detail 2 months ago in this very same room for anyone who might be interested. Okay, so once we have the global data, we're only interested in selecting a grid selection around the equator, which would be our ad hoc, so to say, index of the sea surface temperature. And so we have a lot of data with over a century of years, as I said, and so we need to find a way to organize that data in such a way that it is easily manageable. So what we do, for instance, if we take 1 month of data, we average it in the latitude axis, and then we discretize it in the longitude axis. So once we stack all of the months, we do have a dimensional map showing representing yearly data, which is also winter-centered, since the anomaly peaks do often happen along the winter months, sorry. So once we have that, we perform a principal component analysis to reduce the dimensionality of the problem, and in order also to identify the dominant variability modes in the Hofstadter space. So here you can see the 3 top principal components and that we will use once we extend them into monthly periods for our monthly predictor. And here in the box below, you can see the EOF pattern of the first principal component. And you can see also in these 2 scatter plots how it is highly correlated with 2 other existing indices, which are similar to the one we're using. Okay, so then we need to build our second predictor, which is local, and so it needs to be built for every location. We're using here the sea level pressure data from the NOAA as well. It is a climate forecast system for analysis, and it is available since 1979 up to the present. Okay, so here we are also selecting a grid that is centered at the tidal gauge. This is an example for the San Diego tidal gauge. And so the process that has been followed in order to obtain this predictor is the first, we need to select the red nodes corresponding to the sea. So the land ones, the blue ones are discarded. And once we have done that, we can calculate the sea level pressure squared gradients. And with those, we apply the principal component analysis. And then we only select the principal components that explain 98% of the variance. In this case, for the San Diego, we are selecting the first 4 top principal components. So from that, we could calculate the monthly mean daily indices. And after removing the seasonality, we finally obtain the monthly mean principal component anomalies, which is our second monthly predictor. Okay, so once we have obtained both predictors, we are ready now to build or define the regression model that we're going to use. And as you can see, well, it is a linear combination of both the sea surface temperature and the sea level pressure predictors, as well as the super wave for the sea surface temperature. So that enables to to be able to characterize also the seasonality within that predictor. And this is solved with the least square method by obtaining all the covariates that optimize this function. Okay, and the last step would be to validate the model with a cross-validation in order to confirm that the model is not over-parameterized. And the methodology is, I think it's familiar, and it is based on just by selecting the training set, which is the whole length of the records that is available for each tidal gauge, and dividing it into folds, so we can train the model with n-1 folds, and then test it with the remaining fold, and that would be done for 8 iterations in this case. The results that we have obtained by implementing this model. Here you can see in black the historical signal, and then we need to compare it with the model that has been tested first in red with only the first predictor of the temperature, and then in blue using both predictors. So at the first glance, you can see it is actually a really good fitting, because the extreme values, especially both the lows and the peaks, are quite good, pretty well adjusted, which is confirmed also in the scatter plot with really high correlation coefficients. And this is for the San Diego tidal gauge, which is located in the southern part of all the tidal gauges we're evaluating, which is closer to the equator. If we do compare the results that have been obtained for the Nia Bay, for instance, which is located in the northern, tidal gauge, and it is farther away from the equator, the behavior is slightly different in terms of only considering the sea surface temperature predictor. And it has a lot of sense, really, because it explains that once you get farther from the equator, the dominant predictor becomes the sea level, the sea level predictor. So difference and improval is more noticeable in these cases than for the tidal gauges that are closer. Okay, so yeah, this is what I explained. The evolution and the distribution of the correlation coefficients for all the tidal gauges, and the improvement is higher for the middle upper tidal gauges, which are more distant from the. So given the promising results that we have obtained, there is a potential future for the development of a forecast system within an ongoing project with Scripps, Institution of Oceanography, led by Mark Merrifield. And okay, so that would be what I wanted to say about the model. And I would like to now share and give you a look to Jupyter Notebook that has been implemented with all the code has been programmed into Python. And well, the first thing here is a flowchart, which is easily insertable as a figure. And it is useful for any user that we want to share this code with, so that it is clearly what the Jupyter Notebook actually does and what is the data that you need to provide for it to work. And regarding the libraries that we're using, it is well, they are the basics: Xarray, NumPy, Pandas, and for the particular functions that we're using to solve the main processes is the principal component analysis and the mean squared error from the sklearn. I don't know if that's correctly pronounced, and the line regression list mesh for the SciPy with the SciPy module. And then we display also some of the results with SciPy widgets. Also, there are a bunch of functions that are behind, so that the code is cleaner for any standard user who is not interested in full detail in what's going on. So really, the first thing is to download data, arrange the format, and then, well, it's pretty much what I've explained. The calculation of the monthly mean sea level by calculating the sea level rise, the running mean, and then we would have our predicting here. We would work with the regional predictors, sea surface temperature, then the sea level pressure. We use also Matplotlib for all the plotting figures because, well, I haven't explored yet many of the geographical libraries that I'm sure there exist. So that would be something to explore. And yeah, there's the first model, the fitting one, and the result display of the results of all the covariates. I think I'm going to end here. So if there are any questions, I'll be happy to answer them. And that's it.
So thank you, Sarah. Nice job. So is anybody wants to do a question? Is there anybody? So nothing. So maybe something from my side. What there is a sign in this slide down right. There is a beer and Python and, well, a tree. Which does this symbol stands for?
Pandas. I'm not sure if that's the most recent. I think there's, well, yeah. Okay. Maybe that's, I think I remember well. Or no, maybe it's not. I'm not sure.
Okay, so Thank you, Sarah.
Thank you.
And if you don't want to add any more additional parts to your job, we still have 5 minutes. Otherwise, we can end here and well, we'll see then. Okay. See you then.
Thanks.
Here we go. So welcome back, everybody. We are at GeoPython and Machine Learning Conference 2020. And I have the pleasure to introduce now Martin Christen, which is going to talk about deep learning for augmented reality. Thank you. See you in a minute.
Thank you for the introduction. Deep learning for augmented reality. I put both conference logos here because it's geo-related and machine learning related. I'm talking a little bit about augmented reality. Maybe you, if you know augmented reality, you will think, why Python augmented reality? Makes no sense. We will come to that. But before I start with this, I want to go back in time a little bit and show you the beginnings of augmented reality. I often bring this example of Pepper's ghost. John Henry Pepper invented this basically. Actually, this dates a little bit more back in reality, but it's a nice effect. So we have an actress or an actor down here dressed up as a ghost, and then here is a piece of glass, and the audience see a semi-transparent ghost here, and the other actors, they can go through this ghost, and the audience thinks there are real ghosts there. Most of you know this effect if you know older movies like Star Wars Episode 4. Actually, Episode 1 in that time when Darth Vader and Obi-Wan Kenobi, they turned to so-called forced ghosts, and they used a similar effect there to create those ghosts. In the later movies, of course, this is done digitally, but in the original Star Wars movie, for example, and many other movies where there are ghosts, use this kind of special effect. Let's go a little bit further to 1968. Ian Sutherland created his so-called Sword of Damocles, because it's called like that because if this all insulation falls down, it's not nice for the person under it, I would suppose. Back then, it was not really augmented reality like we know it today. There are some animations on YouTube. If you want, you can watch that. It's a wireframe cube which is flying around in the world. There is no position of this. I mean, this 3D object just flies with the movement of the headset. Augmented reality, like we know it today, evolved, and until the 90s, the early 90s or the mid 90s, there was not much around, and it had some sort of renaissance in the 90s. And then also the term augmented reality was created by Tim Caudle, actually. And in the 90s, there were some other interesting things like virtual reality. Here we have a virtual environment, completely done by computers. And on the other side, we have a real environment. And then there are some things in between. One is augmented reality, where you have computer graphics inside a real environment. And there is another thing which is not that much known today, called augmented virtuality, where we have real objects in a virtual world. So we could have done, if this evolved more, we could have done our conference in this augmented virtuality, where we all go into a virtual room, and some avatars of ourselves would be there. There are some applications even today of augmented virtuality, but it didn't evolve as people thought back in the 90s. So I said 1994 here, and if I say 1994, we have to a little bit think back. For example, if we are in the domain of computer graphics, how did the best computer graphics, or let me say the best computer games in 1994 look like? And that's it. We had some blockbuster games like Heretic, back then there was the Doom, Quake, and all these times this shooter games came up. We had fantastic graphics with Tekken, where you can do some kickboxing. If you look at it today, it's really funny, not more. And titles like Warcraft, yeah, if you look at it today, it's interesting, not more. Back then we had CPUs with 3.1 millions of transistor. Pentium processor came out. That's 1994. So if we go ahead in time, let me show you Flight Simulator, the latest version of Flight Simulator. I took some screenshots. Actually, I copied those. I hope we will not get banned in YouTube for that. Some screenshots of Microsoft Flight Simulator. And if you look at the GPUs, today there are GPUs, of course, and some CPUs. I took a little bit exotic CPU. I took Apple A14 from the latest iPad, which has 11.8 billion transistors. So we go from million to billion. And CPUs or GPUs, they have more than 20 billion, even more transistors today. So that's basically the comparison, and we see the graphics evolved and also the devices evolved. And there is one other thing today. There are some glasses like the HoloLens from Microsoft, the HoloLens 2, and Google Glass, which had some initial problems with privacy. Yeah, and more such glasses are popping up. I'm not really, I don't really like those glasses at the moment. Most I do today with augmented reality. By the way, this one is Magic Leap, I forgot to mention. But most of the glasses today, they are cool, they are nice, it's fun, but they have some disadvantages. I still prefer using the traditional, more or less traditional smartphone approach. So we use smartphones and we augment things. So let me show you some possibilities today of augmented reality, or more or less the augmented reality categories. The classic one is that we have some sort of marker. We take this marker and put it somewhere like on this wheel, which is not really practical. And then we see some augmented things. We can change things in that. Whatever you augment, it doesn't really matter. You can also take some markers which are not QR tag-like. For example, one of our first applications was we take some maps as markers, and then we put a 3D model on top of it, for example, with live traffic, because these devices are connected to the internet, so we can really do some live data inside. And we have different maps and different 3D models, so that's it. This kind of augmented reality is more and more disappearing because markers are fun, but yeah, it's not state of the art anymore. Another approach is to take things like the compass or the GPS or the accelerometer of the device and then try to augment the location somehow. So there are some applications where you can show the actual satellites in the sky. So it's if you use it, you will see a satellite flying around, or you can use the real image and put some tags here in which direction are the restaurants. Of course, there are some problems with which is front, which is back. Oh, I'm sorry about that. I don't know what happens with my presentation. So there is also another category. It's the projection-based augmented reality. This one is also done, for example, in museums. If you have some city models or another model and then you project something on it. Some people did something awful like projecting an old-fashioned keyboard of a mobile phone and then dial the number, which is not really practical. I mean, today with voice recognition, this is much easier to just say the number, but that's of course an older example. or some user interfaces using those projected things is also possible. Another approach is to use outlining-based augmented reality. So you have a real physical object and you alter it. For example, this makeup mirror where you can try out different lipsticks or all these makeup things, which I never understand, which doesn't matter actually to me. And another thing is trying out clothes. I should maybe buy a new t-shirt, so then I can just go into this shop and see how it would look like. And so that's called the outlining-based augmented reality. Of course, there is another important thing, the superimposition-based augmented reality, where you can also take a real 3D object and then augment another 3D object. It's a little bit similar like what we saw before, but it goes into another category. So we can really see through a 3D object. So we see what's inside, more or less. We would see what's inside of this element. So for example, the bones here are inside the arm, so we can really see more. We see through objects. Okay, that's the most important things that existed. And since a couple of years ago, there is a new trend using the localization and mapping approach, the SLAM approach in a markerless augmented reality. So you detect what's around you. You detect there is a floor, there's a table, there are some planes, and then you can actually put objects on those planes. So the real world interacts really now in this case of augmented reality. And there are two big players at the moment. It's Google and Apple. They developed the ARCore and the ARKit. So ARKit is Apple, ARCore is from Google. And with those APIs, which are a little bit similar in a certain way, you can really detect what's around you. Okay, so we tried something in 2018. We used, in this case, ARKit. We used an iPad for that. It was a master thesis where we tried to do all these things outside in a street and augment some pipes from the underground actually. So it's some sort of superimposition based augmented reality. But we put it on top, like in the reality, people use sprays and do that on the surface. So we use those pipes on top of the street and we can see, for example, power lines or whatever, water and so on. This master thesis was done by Lucy Yele. There's actually a movie which should play here automatically, but it didn't. So I hope this is visible. I just realized I forgot to optimize for movies in the, I think I can see it on my second screen. You should be able to see it. So he tried many things, for example, walking far away and see if this remains stable. I think he managed to really go 60 meters and it didn't really move too much. There were some problems with altitude actually, because the street is not really flat. So this is not supported or was not supported back then in ARCore and ARKit. And you see this actually worked quite well. It's stable enough to do it, and we had accuracy of about 30 centimeters, which is not the best, of course, but it's acceptable for most use cases. So we improved this one. After that, after this master thesis, we made a project with the local power company, IWB, and two cantons in Switzerland, Basel-Stadt, Basel-Land. They were very interested in this technology to improve it and to use it for their own data. So we created a small application. Actually, it was a big application with thousands of lines of code. And here is an example. So the operator takes his, in this case, iPad, and goes outside, walks around here, and the system calibrates. Actually, it's a manual process. I will come to that. And then after this calibration, we see all the pipes, and it's connected to a WFS server, web feature service. And we also have some other data sources. And yeah, we can change styles here, transparency, for example, and so on. I will not show the whole movie, but you get the idea. So here are all the layers. It's a traditional web feature service, and the biggest problem was compatibility. One canton had the version 2.0. No, it was actually the power company who had the version 1.0, and the others 2.0. So we had to be creative there and do the best. So we see this worked, but we were not quite happy because initially we had to manually fit the streets, the street data with the map. So we had to really put, actually we created an orthophoto here, and then we had to fit it manually. Where is the border, for example, the pavement border? And that's a little bit difficult step to make for every operator. So we thought, how about doing this automatically using deep learning? So we started a new project with SwissTopo. That's the federal, it's government for topography. And we have one problem. We want to be completely cross-platform. We want to support Android and iOS and so on. And yeah, one problem is, of course, there are some 3D engines like Unity, Unreal. There are some people who prefer developing natively on the, so we have C++ here, we have C# here, we have maybe even HTML and so on. And then we have Unity, which is programmed in C#, or Unreal, which is programmed in C++. And on the other side, we have some things like Android, iOS, or even the HTML-based WebXR, and we would like to support it all. So the basic idea is to create a Python-based smart location API. And this smart location API receives some data from the smartphone and then processes everything, including estimating the location or the position of the device. So if you look at an example here, we have a map data, which is around here. We have two pictures. So the first question is, where exactly are we? So from the GPS, we get this one. We know we are around here. And then the question is it possible if we just see the picture to estimate where we are? So in the case above, we see, for example, here the pavement, and there is this edge here, and maybe we can find this as a human. So we know we are around here. Maybe it's a little bit more. And the only solution would be that this point here is this one or this one. But if we look in this direction, I know we look in this direction because we are around here. So this point here must be this one here, which is a little bit outside this 30 meters, but it doesn't matter. There is only one possibility. And if you look at the second picture, now we have a small problem because it's raining. And if we look again, where could this be? This position here. So the only way is that's around here. Okay, we don't really see that one here in the picture, but it doesn't really matter. So we think that's possible to estimate position out of pictures. So the next step is let's take an existing neural network, because there are many neural networks in the automotive industry now, which detect many things on street level. However, we tried that, and there is one big problem. If we take the so-called pavement perspective, if we are actually on the pavement and we make a photo out of the pavement, so like here, those neural networks don't detect the pavement correctly. However, if we go on the street, it is detected correctly. So this one is not detected as a pavement with most current neural networks, because they are really optimized on the street level. If you are in a car or you are a car and you look around you, then you see here the pavements. So what we did is we collected thousands of photos from the, I call it the pavement perspective. Oh, I'm running out of time, I see. Then we created a neural network using a wonderful service called Segments AI. I really recommend this one to try it out. It's really very easy to create a segmentation. For example, you can really say that's straight. We made about 20 different labels. So we have cars, we have motorcycles, we have trees, we have vegetation, we have many different things. And now the basic idea is to have this smart Geo AR using this photo and create a exact position out of this. It requests a new scene, then it uploads the image planes and point clouds and so on, and gets a position, and this loop continuous, and we have a load balancing on the server, and it works. I'm skipping this movie here actually because we are running out of time. So the next steps are we train the final model, we test accuracy, we use the LiDAR data. We also want to use LiDAR data. We have from many cities, we have a very dense LiDAR point cloud, and we could also use that for additional matching. And in most cities in Switzerland, at least, we have very nice 3D models, and we can also take those for additional matching. So a little bit early still, but doesn't matter. So thank you very much for your attention, and I'm ready for questions.
Thank you, Martin. Nice talk. So, anybody wants to do a question? I'm waiting. So maybe, may I do a question? You mentioned, is this project kind of up and running already, or are you starting it right now, or what's the plans?
It's up and running. It runs until end of June next year. So we are more or less in the middle of the project now, and yeah, it's up and running. We're still collecting new ideas at the moment, and we are ready to do the first tests very soon. So in the next couple of weeks.
Okay. So, okay, no questions.
It's always like this after the lunch break. People are tired to ask questions. No problem. I'm around. You can ask me questions. Of course, there is one actually in the Discord chat. I just seen a
ML track. No, I can't. What?
So the question is, what's the accuracy of the laser? How do you make sure that you not miss the satellite? No, that was actually not talk.
No,
okay,
it's the other, it's the gear.
Okay, no problem. So yes, thank you very much.
Thanks to you, Martin.
And we make a break until the next talk.
Yeah, we will start again in 7 minutes. Thanks, Martin.
Thanks.
So, are we ready to go?
So yeah, here we go. So now, after this small pause, small break, I'm going to introduce Wojciech Dudzik. Is that correct?
Yes, Wojciech Dudzik. I know that Polish is a hard language.
And he's going to talk about how to become painter with machine learning and iOS, Canster app. So that's up to you.
Okay, so I can promise you one thing, that in that next 20 minutes, I will transform you into Van Gogh level painter. But let's start from a beginning. So my name is Wojciech Dudzik. I'm a machine learning researcher at NetGuru, the company located in Poland. I'm also doing a PhD in Silesian University of Technology, and I have the pleasure to present you the work of our team on the Canster application. So first of all, let's start from the very beginning of the painting. So painting started a long time ago in some caves, a few thousand years actually, and through the centuries it was mastered by many people and improved. So now when you want to paint something, you probably require a lot of skills, some training, a lot of time, and also some talent. And when it comes to the talent, I'm rather closer to drawing this sticky man on the right. It was even hard, than drawing like the Van Gogh on the left. But still, there is some hope. So we can just become a copycat painter. Yeah. So we have some content image on the left. In the middle, we have the style image, and on the right, we have the desired output of applying the style to the content image. So we will not create a new style, but we will paint really fast. So all of that is possible thanks to the first work of Gattes and all, started in 2015, a neural algorithm of artistic style. So the basic idea in here is to put those two images, the style image and the content image, through some kind of convolutional neural network, then extract the features from the different layers of this network, in such way construct the loss function and optimize it for applying the style to the content image while still retaining the content of the image. So there's only a small thing in here. A single image was taken from 3 seconds to 3 minutes, depending on some settings and the image resolution. And we are talking about real-time application. So a few years later, there was another work, which is the basis of most of the real-time style transfer works, which divided this concept into two parts. So we have this image transform network on the left, and on the right, we have the loss network, in this case, VGG16. And as you can see, this transformer network only gets the input image, do the forward pass, and produces us with some output, which then is assessed by the loss network, from which we extract the style loss and the content loss from different layers. So this losses is basically, they are very simple. So we take all of the features from certain level of the network, in case of the content part of the style loss, and then calculate just mean squared error. In case of the style loss, we calculate first the Gram matrix and then the mean square error between those matrices. And at the end, our loss function is just the content and style, for which we need to apply some weights. So in Python, it looks more or less like this. Additionally, each of these layers can have its own weight. So for example, some, let's say, deeper layer of the network can have a little bit more weight for the output of the loss function. So going further, there's this comparison of the results. So in the middle, we have the Gattes and all work, and on the right-hand side, we have this Johnson's with the real time transfer. here capitated as hours. So both of these networks give us pretty nice results. The second one gives also real time. So let's just jump quickly into this real time calculation. So we can see that for the small images, 256 by 256, we have 15 milliseconds. So that is very nice, around 16 frames per second. So we can probably progress, but there is a little bit catch in here. Those methods are benchmarked on the GTX Titan X GPU. And I'm not sure if you know how big those GPUs are, but they are not very portable. So still the style transfer application would be limited when we are talking about the mobile application. So it's great that we can have these methods on the graphic card, but we really like doing things on our phones. We have these phones almost always in our pockets. So let's just for now get a quick break and ask ourselves the question why. Why starting with the iOS? Why starting with all of this mobile development? So first of all, we want to create a nice tech demo, learn ourselves with all of these methods and techniques. And there was also this small chance that the application can go viral. So the basic idea, instead of just applying style transfer to some video, which is rather a common thing, we wanted something more. So we think about a portal that you can enter the painted world. So in order to do that, we also wanted to use the augmented reality. So I'm sure most of you more or less know how it works. With the help of our mobile devices, we can put some 3D objects into real world and combine it into a single viewpoint. So another thing is that these techniques are still under development. So for example, in the new iPad, there will be a LiDAR support, which will increase the resolution and accuracy of this mesh that is created for the augmented reality. So there's still development in there, and we think that it might improve many applications in the future. So also another thing is that R is not very hard thing to do. Here is the few lines of Swift code that enables to put such a box onto the floor. So it's not something that we need to be afraid of doing. So here is the fun, where the fun part starts. So we thought about creating this portal and applying, and here is the very first demo of something that worked more or less in the way that we wanted, where there's still a lot of issues about this. And we'll just resolve them later. As you can see, there's a lot of flickering in here, and all things are blinking. So when it comes to the bumpy ride to the solution, testing all of the different parts of machine learning can be hard. As I saw on this conference, a lot of you likes to use Jupyter notebooks. And when we started this project, we also didn't want to create all things from scratch. So there are already repositories which implements this research papers that I introduced at the beginning. But it turned out very quickly that there's very different settings when it comes to all of these machine learning things, to the libraries, to the versions. It does not work together with each other. So we got a lot of pieces to play around, but we need to untangle it into a single solution, as we wanted to deliver probably more than a single model for the mobiles. So in order to that, we created a very simple pipeline when we have configuration stored in the JSON files, which is automatically then trained, and the training ends with exporting the artifacts, so the models, also some images and videos. and also converting it to the proper CoreML format for the iOS developers, and then exporting it also to the Google Drive. So after that, the iOS developer can just go to the Google Drive, download the model, build a new version of the application, and test all of that things. So going further, there was one issue that we met with this work. So there is this flickering. This method was created for the still images, and it works really great. But when you apply it to the video, you can see that all of the blinking around the dog. So actually, there's also style transfer for videos which solve this problem. There's just a little problem that it uses the optical flow, and to be more precise, dense optical flow. So dense optical flow is rather costly to calculate, and there is no way that we can do it in real time with the smartphone. So going further down the line, we found that we can also put this temporal loss into our network. So I will dive into the details about the network in a few minutes. But starting in here, we have the same content and style loss, but we also extract some features from the middle of the network, save it from the previous frame of the video, and having the data for this dense optical flow and some occlusion mask, we can calculate these temporal losses. So now the issue in here was that normally when there's no temporal coherence introduced for the network, the two images can vary with some shading, some different colors. And when you run it on the video, it starts with all the flickering and color changes. So our network was this convolutional neural network. First started with a few layers that were downsampling, the residuals, and at the end, the decoder part. So in here you can see also the comparison with the number of filters related to the work of the RicoNet, which introduced these temporal losses. So as you can see, we already created the network that is much smaller in here, and additionally put the parameter of beta for the number of residual layers and alpha for the numbers of filters in those layers. So we think in here you can see also the final loss when it comes to this temporal coherence. So there's this two equations. The first used by the previous works, the second one used with the temporal coherence calculated in here from the two frames apart. So we already solved the problem. Yes, we have the proper method, proper network, and so on, and that's great. But there is also a big gap between the academia and the business. So we found out that even though those things were well described in the paper, we implemented, and then this happened. So on the left we have a single frame from the very first method, so more or less the expected results. In the middle we have the thing that came up with the temporal coherence introduced. So we have these washed out colors, and with another methods we also have the artifacts that were that in order to solve them would need to implement a custom layer, which is also not supported on the mobile devices. So there's many problems with achieving that. So we came up with somehow improved loss. So first of all, we trained this network with the loss, the first loss visible in here. So only the content and the style. And then after the network was already trained, we, let's say, fine-tune it with the temporal coherence. So naturally, this network already had the proper style that we wanted, that we were also able to control, more or less. And now we only needed to fine-tune it for a few epochs to introduce this temporal coherence. And that's the end result in here. with using this approach. So as you can see now, especially in the sky, more or less all of the things are rather stable. So going further, measuring performance, we created a special app for that. And here are the results. So first of all, the work of Reconet, from which we then started, had network that has size of few million parameters. First thing with which we started have only 500,000. And then we also downsample it even to the size of the 4K. And as you can see in here, achieving real-time performance on mobile devices is possible, even on the older model of iPhone 6s, with the proper size of the network and also rather smaller resolution. So here what it looks like on the chart when it comes to the number of parameters. So something between 50,000 and 100,000 parameters are the desired sizes. Because also in here we can see the qualitative comparison of these results. So on the right-hand side, you can see the smallest network in here, which introduced a lot of different artifacts. Not all parts of the image are visible well. So basically assessing this qualitatively, we choose networks from these rows, which had a nice spot between the real-time performance and also good looking, because even with when we enlarge this image for the full resolution, probably there is very little difference between the biggest network with 500,000 parameters and the one that have 50,000 parameters. So and here you can see now what the final result of our application was. So putting this portal somewhere even in the middle of the forest. One more thing is that the issue of the flickering, actually for some users that we asked, this flickering was a nice addition, at least for some level. So we needed to control how much flickering we can have to seems like all of the image feels more alive, and which level of the flickering starts to break the user experience. So going for further for the lesson learned in this project. First of all, I would like to say that machine learning on mobiles is different. So there are many operations that are not supported, which provide us with some difficulties during the building of the application. When it also comes to the two most popular frameworks, so the TensorFlow and the PyTorch, we managed to do this with the PyTorch and some conversions between the formats for the CoreML. But actually going for the Android would be a little bit more difficult because this type of conversions between the PyTorch and TensorFlow introduces some additional layers which heavily impacts the performance and break the real-time promise. Another thing that we learned from this project and that I want you to know is set the clear goals. In our case, we cannot measure the performance. So normally in machine learning, you can measure maybe accuracy, some other metrics. So we have the hard number to compare and improve. But in here, we faced also situations like this. So we must rely on the polls among few dozens of workers in our company that will tell which effect they liked actually better, because it's hard to measure which style actually can be better. Another thing, because this was somehow a learning project and also an R&D, we have a frequent team rotation. So I will encourage you to create a proper documentation for all of your colleagues. I know that this might not be a very popular opinion, but I think that this kind of documentation help us a few times with some bugs. Never underestimate the yellow duck and pair coding. As it turned out that there are things that we can easily misunderstood between our teammates. So going for the summary, working in diverse team is very fun. So communicating with, from the machine learning perspective, with all of the mobile app developers and how they see things. And machine learning in iOS actually with the Core ML is easier than you think. So a lot of operation is still supported. It's easily to run it on GPU. With a little bit more work, we can run it on the newer models with the NPU, so the neural processing unit, which enhance the performance even further. So that's the key thing I want you to know. So at the end, as I promised, if you want to become the painter now, you can download our application. So thank you very much. Are there any questions?
Yeah, that's question time. So maybe I should start one. We have not so much, but enough. So in order to recap, do you train the models in the cloud and then you upload those in Google Drive? Is that right?
Actually, yeah, but it was not in the cloud, but on some server of our own. But okay. Basically, yes, we trained it with, I think, 1080 GTX of NVIDIA. The training took around 3-4 hours for single configuration. So that's not a very long time.
Okay, so then the app downloads the model and then runs it in real time.
Yeah, so the process looks like first we export this model into the Core ML format, and it cannot be downloaded directly into the application. It needs to be put there by the iOS developers. So there's also this possibility for the improvement of downloading the models, but we didn't want to do that as the quality of different models can vary greatly. So we wanted to achieve some, let's say, good quality of these models. Yeah. So we trained actually for single model to put on in the application. We probably tested like 20 to 30 configurations each time.
So then you ship a new version of your app, basically.
Yes, okay. Exactly.
So I suppose you automated the entire deployment cycle, continuous integration cycle. Okay. Well,
there's still this one manual step. Yes.
Well, it should be, otherwise. Yeah. So I think there are no other questions.
Okay, so still, if there will be any, you can always catch me on the Discord channel. So okay. Thank you very much.
Thanks to you. So see you next time.
See you.
So now there is a coffee break, and we are gonna be back at 3 and 5 minutes. So that's my last presentation for today. So cheers. See you next time.
Hello.
Hello.
I need to check my audio setup quick.
Yeah, I should check also if I can share the screen. Can I start? So I can do with the. So can you see my screen now?
Yes, we can see a screen. Okay, welcome everyone to the, I believe, last session of this day. And it's my pleasure to introduce Alba Recondo to you from the Universitate Cantabria, as I see here. And she's gonna abduct us to the Pacific, which is something that most of us probably haven't been able to, at least in the past half year. So the stage is yours.
Okay. So hi, my name is Alba Recondo. I'm a PhD student from the University of Cantabria working at the GeoCean Engineering Group. GeoCean is a small young scientific group working for the development of open source statistical and hybrid tools for the coastal flooding assessment and forecasting. The majority, sorry, I'm gonna see if I can. This. Okay, so the majority of the projects we are involved in target the Pacific region, a region with numerous low-lying islands and archipelagos that are constantly threatened by wave-induced flooding due to tropical cyclone and distant source wind waves. So, as in the coming decades, the tropical cyclone intensification and sea level rise due to climate change is expected to increase their exposure and so their susceptibility to coastal flooding. It's a priority to develop new strategies for an integrated coastal management. So if we locate or if we imagine that we are at a particular point in the Pacific Ocean, as it can be the Marshall Islands, we know that the waves are mostly generated by winds, but there are two kinds of wind generation. One is the local wind generation, and in this region what we have is constantly blowing easterly trade winds. And the aspect of a sea or wind sea, as the community of coastal engineering call, is this in this picture. So it's a collection of irregular short-crested waves, and we represent the energy distributed in this sea state by means of a wave spectrum, and is what we are seeing in the lower right, on the lower right side. So we see that the energy distributes in a wide range of frequency and directions. On the other hand, we can have storms that was generated in the northern hemisphere and was generated maybe days ago or weeks ago, and the energy travels across the Ocean Pacific along with circles, and finally reach the point. So the energy when approached the atolls came as a wave system that we call swells, and it's long waves. They're long waves coming in a regular sequence, and the energy distributes in the spectrum in a narrower area of frequency and direction. So the methodology that I'm going to present, that I'm going to introduce you now, takes into account the whole energy of the spectrum that can appear in the spectrum. Because if we take a look at the ocean, at the Pacific Ocean, we can easily realize that we are not going to have only one swell approaching the Marshall Islands, but we are going to have multiple directions of swells coming from the northern and southern hemisphere. So the methodology is titled hybrid downscaling. So downscale means to transfer the wave information from deep waters to near shore by increasing the spatial resolution. So we can distinguish between dynamical downscaling or numerical downscaling and statistical downscaling. So the dynamical downscaling, it's when we numerically simulate the wave processes, the wave transformation processes, by means of grids of increasing resolution. So we can go from a global to a regional scale, from a regional scale to a local scale of maybe 50 meters, and finally from a local to the inundation extent. But the high computational cost that this dynamical downscaling requires makes necessary to introduce or to add new statistical methods, and that's what we combine statistical and numerical, and finally get a hybrid methodology. That is what I'm going to present. So the start of the methodology is historical available databases, which we apply a spectral partition. Then we apply a meta model that combines clustering algorithms, numerical simulation models, and finally interpolation techniques to finally get a proper characterization of the wave climate around the islands. This methodology I'm gonna present from historical databases, but it also set the basis for future projections and for accurate forecast systems. So the methodology starts by looking at the available databases. So we basically have a global wave reanalysis or global wave hindcast formed by nodes around the globe, in which we can extract the spectral wave information that is going to be the input for our hydraulic boundary conditions. We have this spectral global information in nodes maybe of 40 kilometers of resolution. And also, if we are lucky in our regions, we can have in situ wave measurements as buoys. So zooming our study site, and here I'm gonna talk about Mayuro and Arno Atos that were in a project that we also done. So if we take a look at the available stations of the global wave hindcast that are around the islands, we can aggregate the incoming wave partitions to only a single one, that is the one that we have on the right side. So we are doing this by splitting each spectrum, each frequency direction spectrum of each station, splitting it in 60 degrees sectors that points at the islands, so that we don't lose any spectral information and we avoid shadowing factors. And so we have the entire information into the 6 stations. We have aggregated the information into one. Once we have this series of C states, because the global wave hindcast that we have available is 40 years of hourly C state. So now we have 40 years of hourly spectrum C states. Next step is to split or the whole wave energy of the spectrum into the wave partitions. So to this end, we applied a physically based techniques to identify swell trains. And we do this by means of the wave spectral library developed by MetOcean Solutions. So in this library, the watershed method is implemented that looks for the crests and valleys of the spectrum. Basically, we can define the number of wave partitions that we want to select. And finally, we parameterize each wave system by means of 5 parameters that for the coastal community are used for characterize the sea state, the energy in a sea state, that are the significant wave height, the peak period, mean direction, and 2 parameters that refers to the shape of the spectrum. So we have converted the complexity of the spectrum in cells of frequency direction into 5 parameters. So taking a look at the data collected till now, what we have is 40 years series of the hindcast, of the global wave hindcast, that we have parameterized into 5 parameters. So we have finally 350,000 of C states that we multiply by the number of wave partitions that we wanted. So assuming that each C state takes at least 10 minutes of numerical simulation to propagate along the different grid resolutions, we have a total of 7 years of simulation for a normal laptop as the one that we use for our work.
So due to the unfeasible character of this dynamical downscaling, what we add to this dynamical downscaling, the statistical tools and data mining techniques. So to reduce the dimensionality of the data set, what we apply is a MDA selection, that is maximum dissimilarity algorithm, that starts by selecting in the n dimensional data set the most dissimilar case. And so it is a iterative procedure that ends till it reaches the number of cases desired. So typically for the coastal projects, the number of cases that we select are 500 cases. So we are reducing the data set of a data set of 212,000 cases to 500 cases. Once we have these 500 cases, those are the ones that are representative for the whole wave climate, and so that those are the ones that we are going to propagate. To this end, we apply the numerical simulation model that is called SWAN, developed by the Delft University of Technology, and we do the propagation nesting different grids of increasing resolution. So we can go from a regional scale of 1 kilometer to a local grid of 200 meters or even 500 meters, so that we can have the output of our 500 cases in cells of 50 meters around our interested location. So now we have the data set of the 40 years, the subset of 500 cases selected, and so the 500 cases propagated. So we are able to apply an interpolation technique that we use, the RBF interpolation, that it takes the form of a weighted sum of radial basis functions and tries to interpolate a surface with the minimum local error. So finally, what we obtain here is the global wave hindcast propagated, the 40 years propagated into specific points around the atoll. So in this point, we are able to do a validation in the case that we have available buoys, so data from the buoys in our region. In this project, in this work, we had a buoy in the eastern part of the island, so we were able to validate the methodology, and so the goodness of the validation and flexibility allows us to reproduce this methodology to another islands and worldwide. So as I told in the first slide, the swells approaching this particular point of the Pacific Ocean come from the 360 degrees. So if we split the whole directions into sectors, we are able to do an evaluation of the energy flux contribution of each sector, or we can evaluate the seasonality character or interannual variability, and also the long-term oscillation, and as can be ENSO event. So all this methodology has been implemented by means of a Python library in form of Jupyter notebooks. These Jupyter notebooks the Jupyter notebooks are a tool for a non-expert user that can have internet access to data services, and also can run the machine learning methods that we saw previously. There are codes for pre-processing, running, and post-processing the SWAN model, also to reconstruct the whole time series throughout the island, and also there are kind of outputs, user-friendly visualization of the results. So I would like to jump into these notebooks. So the methodology has been split into 5 notebooks, in which, as you can see, for example, the first one is the definition of the input of the forcing. So we have the spectral input and the spectral partition. So here we select the number of partitions desired, and when the forcing is defined, we are able to apply the MDA algorithm and we also do a distinction between the wind seas and the Suez. So we have an MDA for the seas and an MDA for the Suez. The cases selected are run by means of the model. So we can see here the regional simulation and also the 200 resolution output and the detail one. So the interpolation with the RBF is done, and also we use a validation tool for the RBF that is called the K-fold to assess the capability of the RBF to reconstruct properly the wave climate. We also have a notebook for the validation in case that we have a in-situ wave measurements. So we can have the series propagated and also the series of the buoy. And finally, we have a series of outputs that includes the wave climate characterization in the different points, spatially distributed throughout the island. And so that's all what I wanted to talk about. Thank you. I'm not sure if.
Yeah, thank you so much. I'm going to check now if we have any questions in the chat. There's nothing so far. Maybe on Discord. No, it looks like you answered all questions to full satisfaction.
No, I can now answer the questions in the Discord channel, so it's good.
Okay, so you will be available on the chat and on Discord, and we are going to continue here in 3 minutes.
Okay, thank you.
Thank you so much. It was a very nice talk. Bye.
Bye.
Hi.
Hello.
Hello. Okay, so this we are going to hear a talk now about terrain shading. Is this right?
Yep.
So as you're seeing Markus Heitzler. He currently works for ETH in Zurich, and he investigated this ancient technique of producing really, really pretty maps, and he wants to teach it to computers. So we're excited to hear your talk. The stage is yours.
All right. Thank you so much. Let's try to share the screen. Okay, so you can see this? I guess you do. So hello, everyone.
Yes,
yeah.
Yes, it works. It works.
Okay. Yeah, my name is Magnus Heitzler. I'm currently a senior assistant at ETH Zurich at the Institute of Cartography and Geoinformation. And as Adrian already mentioned, I will talk a bit about cartographic terrain shading with deep learning. And I want to mention that this is actually a collaboration with Monash University in Australia, and also that the very similar talk is actually given soon at IEEE Viz, where there will also be a paper on this topic. So I subdivided the talk in 3 rough parts. So first of all, I will talk a bit about this ancient technique of making pretty maps, as Adrian said. In the second one, I will talk a bit about how neural networks can be used to create similar terrain shadings in comparison to manual ones. And finally, I will talk a bit about the quality of the results and also about the opinions of some experts in the domain. Yeah, so what you're seeing here is a very traditional topographic map. In this case, it was created by SwissTopo, the Swiss National Mapping Agency, and it contains actually all the features that you would expect. You can see rivers, roads, settlements, and so on, but also information actually on the terrain. And this can be either in the form of spot heights, where there's a specific height labeled, or also in the form of isolines that give information about steepness and so on in the terrain. Also, what you can see here is actually a specific symbolization for terrain itself, these dark hatches that also give you an impression already, okay, there might be some sort of mountain. However, a topographic map, as it is depicted here, is not very good at intuitively give you an idea on the terrain. And for that purpose, cartographers usually add terrain shading or relief shading. And here you can pretty directly actually see where valleys are, where high mountains are, and so on. Now, what is actually such a terrain shading? In fact, it's essentially a grayscale image that is blended with the topographic map. And traditionally, they were actually produced with pencil, or also with more modern approaches like airbrush. What you can see here is a sketch made by cartographer Sarah Bell in a very well accelerated manner. And you can imagine that if you want to create a high quality relief shading for a large area, it can be quite cumbersome and takes quite some time of work. So furthermore, you might think about, well, nowadays, maybe there are techniques already that are really good at doing this somehow automatically. And yes, actually, there are already some techniques out there that try to somehow create these shadings. Here on the right, you can actually see one of them. This is simply a calculation or made of based on Lambert's law. So they take into account the slope and the orientation of the mountains and hills, and then calculate the brightness for each pixel, and well, map this essentially as an image. Now the problem is, if you do this and compare it with a manually created one, you can actually see that there are quite some difference in the quality. So first of all, for cartographic purposes, you usually omit a lot of details, so not to distract the user. So, and another issue is actually also that in certain places, you can't really see very well the steepness of the mountain. So for example, if you consider this part here, it looks all gray. but what we actually rather want to have is more contrast also in this domain, as you can see on the left. And let's talk a bit about how actually cartographers achieve these goals when they create manual ones. So first of all, usually they simulate, so to say, a light source that shines usually from the top left of the image, and use this as an idea on where the which slopes should be brighter and which ones should be darker. This is rather similar to the automatic one that exists already. Now, however, if you look at this specific location, this ridge here, it is oriented pretty much in the direction of the light source. And this would mean that actually both slopes would obtain the same gray value, which I already showed you in the automatic image. Now, what cartographers actually are doing to prevent this is they change locally the direction of the light source so that we still get such an expressive image of this mountain. And of course, this is not only done for a single mountain, but it is in fact done for the whole region. So this is one aspect that is not so easily reconstructible with the current approaches. Now, another aspect that cartographers actually are considering is that they divide the terrain in different landforms that are then treated as single entities, and where contrast in itself is optimized. So what you can see here is actually areas that should be shaded in more bright colors, while next to them there are areas that should be shaded in relatively darker colors. Furthermore, you can imagine already it's a lot about contrast itself. So another aspect that is actually tackled is the contrast that depends on the elevation of the terrain. So if we are looking at very high mountains, we can see actually that very high contrast is applied to the shaded relief. And the further away we actually go from the high mountains, we see that the contrast actually is being reduced gradually. So this is also something that we should keep in mind, so that we can easily distinguish flat from high areas. And maybe a final design principle of shaded reliefs is it has to do with generalization. So maps can be produced for different scales, and the smaller the scale, the less detail should actually be visible on the map. So cartographers also try to generalize the terrain, so to omit a lot of information depending on the scale you are dealing with. All right, so now we know more or less where we want to go. Now let's think about how we actually can use a neural network to get there. So we tried in our research quite a few things to produce shaded reliefs automatically. And for example, also neural style transfer that was already mentioned in another talk. We also tried out encoder-decoder networks. And at some point, we actually experimented with an architecture that is called U-Net. Originally, it was actually created for image segmentation of actually biometrical images. So you put in a picture of some cells, and it tries to determine for each pixel if this pixel belongs to a cell or not. And we thought, well, maybe we can also use it actually to make not predictions if there's cell or not, but also just try to make it predict the grayscale value of a shaded relief based on an input digital elevation model. And so this is now the specific architecture that we were using for this purpose. It's still essentially a U-Net. You can actually see that by this U-shaped form of the arrangement of the layers, but we made a few changes to it. And I want to explain briefly how it actually works. So a U-Net is a so-called fully convolutional neural network, which means that the majority of the layers actually consists of convolution layers. And this means that a set of filter kernels are trained actually to get from one image to another image. And in our case, of course, it is intended to produce a set of filters that somehow convert the digital elevation model to the corresponding shaded relief. Now, what we are doing is we are subdividing a terrain in different tiles, in this case, consisting or having the dimensions 256 times 256 pixels. And we want the neural network actually not to predict for the exact same resolution or for the same extent, but only for a smaller inner area, because we think that in the outer areas here, it is not possible for the neural network actually to get enough context information to come up with the correct grayscale values. So that's why we are actually cropping the image in the end and only let the neural network make predictions for the inner part. Now, you can imagine that actually only applying convolutions, so filters to an image, does not account very well for the context at a specific location, because these filters usually have a very limited extent, such as 3 times 3 pixels. But the color of one position on a DTM or of a shaded relief might very well actually be dependent on the DTM at a farther location than that. So what this UNet usually does is it consists of also a so-called contracting path that employs a set of max pooling or other pooling layers that essentially gradually downsample the input tile, at least the spatial extent of the input tile, until we get in the end a very compact representation of the input image, such as 8 times 8 times 256 dimensional matrix. And this very compact representation of the input tile needs to be scaled back to the extent that we are interested in. And this is then done by the counterpart of the contracting path, which is called the expanding path, which employs a set of, essentially upsampling operations. Now, if the neural network would only use these two approaches, then the result becomes very blurry. So the trick of the UNet is also to actually copy activations of the distinct layers of the contracting path to the corresponding matching dimensions of the expanding path, as you can see here. And that way, the neural network is actually able to combine very compact representation information and relatively uncompressed information in one go, and can make can reason about the combination of both matrices. Yeah, we also changed, of course, a bit the extents of the input images and also the output image, of course, to only have one final cropping operation here. This is something the original UNet doesn't do. It employs a lot of cropping in between to make the image match every time, just a smaller modification. And what we're also doing, we are including a lot of dropout, so avoiding overfitting. I'm aware that dropout and convolutional layers are not a very intuitive combination of things, but we found that it actually works quite well. And I want to show you what happens actually if we wouldn't use dropout or wouldn't use dropout too much in the neural network. So here are a few images of generated terrains. So if we don't use dropout, we actually get a lot of noise in the output image, or there's a high probability to produce such noise. We were also investigating different weight initializations, and we found that actually the He initialization works best, because somehow if we don't do it, some areas remain sort of flat when we produce results. And on the right, you can actually see how an image looks like usually when we are employing dropout and the specific type of initialization. All right, so this is a Python conference. So I want to briefly talk a bit about what software we are using. Of course, Python. Then we are using Keras and the TensorFlow backend. And of course, this is also based on NumPy to some extent. For image processing, we use OpenCV, and for reading actually the elevation model and the shading pictures, we are using Goodle or GDAL. But we are also using actually a bit of Fiona and Shapely, as well as QGIS. And you might wonder, well, where do QGIS and Fiona and Shapely come into play? And the reason is the following. So what you see here is actually a screenshot of QGIS on the right. And what you also can see here is that actually the manual shaded relief we obtained from SwissTopo is a bit cropped. So we can't really use the whole area to train our neural network. But what we can do is we can define manually where to sample actually the shaded relief from. And for that purpose, we are using QGIS. So we are essentially drawing points on the different locations here on the shaded relief. And then we are cropping the part around these points and use them for training. And this is then done by Fiona and Shapley when assembling our training data. Yeah, some words about training. Usually we have around 100 to 200 training samples. It depends a bit on what kind of resolution we are using. We got, for example, good results for 40 meters resolution. As already said, the shaded relief and the terrain model are both obtained from SwissTopo. We are also scaling the terrain heights and the shaded relief to the range 0 to 1, because neural networks don't work so well for very high values in the input domain. And we train for, well, we experimented with different amounts of epochs, but we found that it works best for 1,000 to 5,000 epochs. We're not employing any early stopping usually, and it requires around 1 to 5 hours on an RTX 2080 graphics card. What is also quite interesting from my perspective is that for loss, we use mean squared error, but it doesn't drop much during training. It starts maybe at 0.3 and then goes down to 0.2 or something, but it's really important to measure the quality visually from experts, and you can't really rely on this loss metric too much. All right, so now we have our trained neural network and we can make predictions with it. As I said already, the output is limited to 156 times 156 pixels. And if you want to render a whole DTM that is larger than that, we need to assemble the tiles next to each other. And as you can see here, we get actually some discontinuities if we do so. So this is something we don't want to have in the final image. And to avoid this, there are two tricks that we can use. Either we use alpha blending, so we are essentially letting these tiles overlap a bit and then use alpha gradients to blend them together. Or we can also change the input and output dimensions of the neural network. This works because it is a fully convolutional neural network and it only consists of filter kernels, and they are pretty much image size agnostic. So this works also, but it is a bit more memory intense actually. Yeah, now we can compare it a bit, how it looks like for a region it was also trained on. So on the left, we see the Landeskarte 200 crop from SwissTopo. On the right, we see the corresponding neural shading. And we see that it actually removes a bit of the details, as you can see here, for example. But it is very good actually at well, smoothing the terrain and also giving a similar impression actually as the original SwissTopo map. So this is already pretty encouraging. Now, as I said already, we also are interested in somehow being able to generalize or produce relief shadings on different generalization levels. And there are also two approaches to accomplish this. So the first one is actually just to change the resolution of the input DTM. So if we give it only a resolution of 120 meters, of course, there's not so much information available and it will produce a more generalized terrain. That's rather straightforward. Another approach that we can do is actually during training, changing the resolution. So we train two different neural networks, for example. And in one case, we train it on a cell size of 100 meter and once on a cell size of 50 meter. And because this one has a higher resolution, but the actual information content is not really higher than in the 100 meter case, the neural network must learn to generalize from to avoid information from the many pixels that it gets from DTM to obtain the the corresponding shading relief. So these are two ways to obtain generalization with neural networks. Another thing that needs to be done with care is actually the normalization of the terrain, as I said already. So for Switzerland, we scale the terrain to the range, the heights to the range of 0 to 1. But if we go to another region, such as northern Poland, where it's very flat, and we use the local heights and scale them to 0 and 1, then 1, although it would be very flat in Poland, would correspond to the very high mountains in Switzerland, and we get this very strong contrast that we don't want to have, but you can see here. So what we need to do is actually to change the scaling a bit of the terrain. So for example, on the right, you see scaling from 0 to 0.2. And it looks more like flat terrain than on the left. Okay, let's talk a bit about the evaluation. So we actually carried out some expert survey, and that consisted of 18 experts that were either creating shaded reliefs by themselves or were doing research in this domain. And they were presented with 10 pairs of shadings. So each of the pairs consisted of one manual one and one neural one. And they were all picked from outside of Switzerland so that it really is applied to a region that the network didn't see already. And experts weren't told which one is actually the hand-drawn one and which is the artificial one. And interestingly, they took quite some time actually to think about these pairs that they were presented with. And the results are also quite encouraging actually. So for our neural networks overall, we got 15% of the times that they were of poor or fair quality. In 32% of the times we got the rating of good quality. And in 43%, we even got a very good, and 10% of excellent quality. So these ratings are actually quite in line with the ratings that also the manual shadings obtained. Another thing that we found is that it depends a bit which region was shaded. So for mountainous regions that are similar to those in Switzerland, we got relatively better ratings. And for flatter areas, we got a bit worse ratings, probably because Switzerland has not so many flat areas where the neural network can train from. So on the top here, you can see, for example, some mountains in Peru, and down here in France. So these got better ratings here than those. Yeah, they were also asked to tell us which shading is better suitable for topographic maps. And in 5 out of 10 pairs, actually, they preferred the neural version. So it was split up 50-50, which is also quite encouraging. One of these cases where they said that actually the neural shading is better than the manual one is presented here for Crater Lake in Oregon. And on the left, you see the neural shading. And they said, well, this is in this case a bit better suitable than this hand-drawn version. They were also asked which version is aesthetically more pleasing. And generally, the answers were similar to the overall preference that I mentioned in the beginning. And one example where they said actually that the neural shading is more aesthetically pleasing is depicted here. So on the right, you see the neural shading. On the left, you see the manual one. And finally, they were also asked to actually say which one they believe is the artificial shading and which one is the manually produced one. And this was astonishingly difficult for them to determine. And here's one of these examples where it was difficult. Here on the right, you actually see the neural shading. On the left, this is the manual one. All right, so with that, I already come to my conclusion. So essentially, we can say that neural networks are really able to create high-quality shaded reliefs. We have a bit of problems to really control the appearance. A lot depends on the training data, and a few things can be changed, such as the normalization of the terrain, of course. But generally, it would, of course, be nice to have a bit more control of the results. However, we think that we can contribute to actually curating cartographic relief shading, as it was done, especially in Switzerland, for a long time. and also be able to bring it to other people to make use of this neural network. And we have to see if we can create some tool out of that, for example. Yeah, and finally, I can just say that what I said in the beginning, there's a paper that was going to be presented at IEEE Vis, and if you want to take a closer look on what we did, I can refer you to this paper. And with that, I'm actually coming to the end of my talk, and thank you very much for the attention.
Yeah, thank you. That was very interesting. I got one question for you already on here on the Q&A, and this is if your code is shared on GitHub.
Not yet, no. I'm not sure actually what this.
Do you intend to like make your models public?
I have to talk with the guys in Australia. Actually, they have a bit the authority over the source code right now. I wouldn't mind. As I said, I have to check with them.
I would have a question for you. Did you just use training data inside of Switzerland and then you applied it to all the other world regions that we saw, like Hawaii and South America?
Yeah, so we only trained on Switzerland.
Because it's the only area where this type of high quality hillshade models are available, or is it?
Good question. I mean, we got SwissTopo was so nice to give us the data, and somehow I'm not sure if that's correct, but some people say it's some kind of gold standard of these relief shadings, and then we just stick to that. But I'm pretty sure this is debatable. But we thought we just try to recreate the Swiss style.
Yeah, sure. I got another question. If you can share your presentation, if.
Yeah, I guess again I have to check a bit with the guys in Australia because it's an adapted version of their version. Yeah, if there's an opportunity somehow in the context of this conference, then I can upload it somewhere. I'm not sure.
I just provided a download link to my presentation on Discord.
Okay.
For the ones that want, but I'm not sure if we plan to actually collect them. I don't think so.
Okay. But yeah, I will check, and if the Discord channel is open for a few days, then maybe I can post it there.
Yeah. I got another technical question. So the tiles that you export, they're actually limited to a resolution of what was it, 152 pixels or something?
Yeah,
length.
yeah, 156. Yes.
And I could believe that the manually drawn model has, like, because it's analog, it's basically virtually unlimited in terms of this resolution. Is this something that was a problem, like recreating the high amount of detail that you have on the highest zoom levels?
Yeah, I think we don't have a single model that really recreates all the details that we got. It always generalizes a bit.
Okay.
But this is also interesting because sometimes you also have a bit of a mismatch actually between the DTM and the relief shading. But
okay. Yeah, excellent. Very nice.
All right.
Thank you for the talk.
Thank you too.
We're gonna continue here in 2 minutes, and if there's any other upcoming questions, maybe we can find you on Discord.
All right. Yep, I will be there. Have a nice day.
You too. Nice. We can see a presentation. That's good.
Hello.
Hello.
Yeah. Hi. Hi, Adrian. Yeah. I was just checking the presentation.
Okay. Are you ready?
Yeah. I'll just get this.
Perfect. Okay. I'm welcoming Shubham Goel. Is that right pronounced?
Yep. Yep.
Now, as our last speaker of this channel today, or actually, I think you are the last talk of the whole conference, because on track 1 we don't actually have a talk anymore. The last speaker canceled there. So we're gonna also have the closing session in this track then, as far as I realize in our organizing group. So you have the honor to present us with the last talk. You are from Triangulate Labs, and I think currently at the University of Illinois. Is that correct?
Yeah, that's correct.
And we're going for hurricane damage estimation. So be prepared for violent winds. Stage is yours.
Okay. Hello, everyone. This is Shubham. Thanks, Adrian, for the nice introduction. So I'll be talking about hurricane damage estimation. So the idea of the talk is to introduce you to the problem, which is that hurricanes cause a lot of damage to humanity, as well as like in terms of property costs, environmental loss, as well as human lives. And if that change in the property damage is detected in a proper way, then it might aid insurance companies in helping out those who suffered the most in the best possible way. So this will be the agenda for today's talk. We'll go through with the introduction, that is change detection and how to go about solving it. We'll go next. We'll go through Siamese networks, which is a technique to try and model change. The next part would involve capturing the data, like the steps required to capture data, because for this kind of a model, you need the images for the right after the hurricane occurred and images prior to that to model change. And eventually we'll go through the post-processing and we'll look at the results. So I'll go through an intro. I'm a final year graduate student at the University of Illinois. And previously I've spent 3 years building deep learning products, mostly in the computer vision space, having built products related to satellite feature extraction and rooftop classification. I like technology, startups, football, music. So you might want to say hi at my Twitter, which is shubhamg_, or my email. We'll get to the problem. So as you can see, the image on the right is how the Hurricane Harvey destroyed this region in Texas. So you can see a lot of the houses are completely destroyed and surrounded by water. And these are explicitly the kind of people we'd like to help out in the best possible manner. Because as of now, the insurance claims are largely very irrationally given out. So it's usually a 3x of the original property value or something like that. There's no quantitative work done on it. So we'd like to detect this change, and whenever we see this change, we try to model it using a technique which should have some desirable qualities. So those are that it should be able to detect relevant changes and ignore the other ones. So for example, there's a natural growth of trees and buildings and other things across time, which is not really relevant for for a problem like this. So we'd like a technique which does not take into account these factors and only is only able to focus on the actual damage. It should also be robust to different lighting conditions and angles, because imagery is captured at different angles, as well as the lighting could be different. And the final thing is that it should be modular. By modular, I mean that parts of it should be we should be able to use pre-trained weights for parts and eventually build our model. So the training data which is being used here is provided by XView2, which is a public data set of over 850,000 building polygons. These are manually annotated buildings which have a semantic segmented mask available, as well as a damage score for each house individually. The damage score ranges from 1 to 4, 1 being completely undamaged, where the building, including the roof, are largely undamaged and there's no water surrounding it. Minor damage would include there's some partial destruction to the house, as well as there's some water surrounding it. Major damage is when most of the roof and nearby area is completely broken, as well as the building is surrounded mostly by water, and completely destroyed is when the building isn't even visible after the disaster. So these are this scale is given by FEMA's guidelines. So this is the only data set available which has made the effort to do this kind of a quantitative damage scaling for houses. So as you can see on the images, showcase a pretty hard-stricken area of Texas, where almost all buildings are completely destroyed. Now we come to how we could model this kind of a change and be able to detect whenever there's damage. So the major component of a Siamese network is a shared convolution neural network, which is able to extract out relevant features for both the pre and the post imagery, and then is able to compare them using a pixel-wise Euclidean distance. Like the distance could change as well as the loss, but the major component is that the CNN being used has shared weights and is able to extract out a higher order feature map, which has features which are relevant to our use case. So for our case, it should have features which are very different if the imagery is if the houses are destroyed, and the features should be similar if there's very little change in the imagery, except for the natural changes occurring. So this is how we've gone about doing the training. So in the first stage, the objective is to extract out buildings which were initially present. So only once we have those buildings would we be able to assign a damage score to them. So that is being done using a unit-like encoder-decoder architecture. The major part is that the post-disaster imagery are not used here because they are not pure enough. There's a lot of damage. So in order to train a good building localization model, those should be neglected, which is what is done. The loss function which has been used is a combination of dice and focal loss. Once we have this trained network, we use the encoder part of it as well as the decoder part to and we convert it into a Siamese network. So what we do is we take the same network and we apply it to both the pre and post imagery now. And then the last decoder layers feature output is used for both imagery. and the difference between them is then input into a loss, which is a different kind of loss now, which now includes cross entropy loss. And since the number of pixels for which there's damage, the damaged pixels would be the ones which have 2 to 4 values, and the undamaged one would be 1. So the damaged pixels are very little as compared to the undamaged ones. So we have to use a higher weight for those class for the model to learn something relevant. We've trained the Siamese network using a combination of dice loss, focal loss, as well as the cross entropy loss with a modified weight. So one big component of this pipeline is that once we have this trained data, the model is not as useful because what we are getting are just the damage scores for the houses and not really dollar amounts, which we would ideally like. So what we would like is for every household which we have detected damage for, we'd like to assign it a ballpark dollar loss value, which should help in insurance claiming. So the next part covers how we've gone about doing that. So now that we have a trained Siamese network which outputs building polygons as well as a damage class for each of them, we take a small business administration data which contains insurance claims filed by people after Harvey, and it contains the actual property value losses which they suffered. So we are now using this as well as the tax rolls data which contain the property values of those houses, and we can kind of take the ratio between those two and check to see it matches with the Siamese network's 1 to 4 damage classes output. So this is the next part of the talk covers how we are in the process of doing that. So we have roughly 53,000 rows for this data. So now this is how we've acquired the inference data. So it involves acquiring first the pre-Harvey imagery and after that the post-Harvey imagery. So the pre-Harvey imagery has been acquired using USGS Earth Explorer, which is a free service. The regions which we've selected are based on the density of the small business administration dataset. For the same region, we have acquired the post-Harvey imagery, which has been made freely available publicly via NOAA's storm source. And all the tiles which are downloaded from there are merged. In some instances, there's an extra alpha channel which is removed, and we have RGB imagery, which is what our model requires to be input. We are using a library named Solaris to generate individual tiles of shape 1024 cross 1024. And we are using these tiles to input into our trained Siamese network, and we are obtaining predictions which do not contain any geospatial information as of now, but we have tiles and we have predictions where there are multiple houses, some of which might be damaged, some of them have there's no damage. Once we have those predictions ready with us, we are ready to move on to the next stage of post-processing the predictions. So during the stage of generating tiles, we are obtaining georeferenced tiles, which are then being stripped off of their location information. So with the process outputs, we are again georeferencing them using the corresponding TIFFs we had generated in the previous stage, and we are merging them together using GDAL. Now these are rasters, and we'd ideally like them to be of vector format for us to apply vector operations in the latter stages, which is what we do. And now once we've done that, each vector only has a single damage score now. And we check for invalid geometries, which somehow creep in, and they are removed. And now that we have a vector polygon data with damage values, as well as the SPA point data, which has dollar amounts insurance claim filed for insurance claims, we merge those using a point and polygon test. So these are the results which we have. So the localization score we obtained was 0.88, which is pretty high. And the damage score, F1 score was 0.79. The combination of those two is able to yield an F1 score of 0.82. We are in the process of obtaining our results, eventual results, which is what we would ideally like, as they are the ones which would help gauge the value which people have lost. So stay tuned for that. These are some of the current challenges which we are facing are automating partially manual portions of the acquisition stage, as well as the post-processing stage. So as of now, we are manually looking at some of the dense regions of the SPA data set, and then clipping our tiles according to those needs, because otherwise the data set size becomes too big very quickly. And this is also another step which we'd like to evaluate results for, is over a bigger region of Texas, and which would even further validate our results. And the last step is something which I've already talked about, which includes comparing the damage ratio to the network's output, so that we have a sense of how well our model is actually working when we compare it with the dollar amounts, and not just the FEMA damage scores. I think that is it for my talk. If there are any questions regarding any of this or anything random, I'd be happy to take on them. And these are the references. And like, if you'd like to get in touch, we could connect over the following channels.
Hello. So this is great. Thank you for your talk. And I'm going to check if we have any open questions now in the Q&A session. It doesn't look like it. And also on Discord, so far, there's no questions. YouTube neither. So I think we're good. It was thank you a lot. If someone still has any open questions, I'm sure you're still around on Discord for a bit.
Yep, we can connect over Discord.
Okay, thank you so much. So I think we will all thank you again. We're gonna have a short coffee break now, and meet in 7 minutes at 4:20 for the closing session. See you then.
Welcome to the closing session. We are already at the closing session of GeoPython 2020 and the Python Machine Learning Conference 2020 online. And here are some statistics. We had a total of 46 talks, including workshops and lightning talks. Okay, lightning talks could have been a little bit more. It's fine. We had around 160 participants, and now we have around 32 plus hours of video to cut. And attendees were 50% on Zoom, 50% on YouTube. Exact stats I didn't yet check yet, but it looks like that. And I'm sure some people had two YouTubes open at the same time because it's convenient, of course. So at this point, I would like to thank again all the sponsors, especially JetBrains, the Python Software Foundation, the EuroPython Society, and the Python Software Association, Germany, Austria, Switzerland, and of course our media sponsors, Triolabs, Manning, and Capital Bay, and the local, which are not real local sponsors this year. And really a special thanks to all the organizers and volunteers this year. We had Nicoletta, we had Matusz, Antonio, Adrian, Sangashanan, and Anmol. And I hope you liked this, let me say, strange setup with Discord as a chat client, including the registration bot and then after registration, the virtual conference channels. Yeah, so my personal impression, it was a new thing, of course. It was my first online conference. It a little bit felt like the first GeoPython conference in 2016. I don't know if you have people in the audience who were at the first GeoPython 2016. And also a little bit, it felt like the first conference, international conference I hosted was the WebGL Camp Europe in 2012. And yeah, there is still much room to improve, of course. We had some issues, especially we had too many, in my opinion, last minute cancellations of speakers, maybe of technical issues or other issues. Doesn't really matter. It was too much, in my opinion. So that was not that good. But still, I would like to thank you all attendees, all speakers, all volunteers for taking part in this really big experiment. And I would be glad to get some feedback. You can send us feedback to info@geopython.net. If you have any feedback, I would be happy to do that. If you do that. So what's next? We will edit all, actually cut all movies and edit them and put them on YouTube, unlisted on YouTube. We will not put them to the public yet. So you will get an email as soon as all movies are published there. And then speakers can decide if you want to go public or not. If you don't like your presentation, you can say, no, the sound quality was too bad, the video quality was too bad. I don't want this to be published, or maybe you just don't want it to be published. So you can decide that later. So the big question, usually we announce the next conference. So what will be GeoPython 2021? What about Python Machine Learning 2021? And I have to tell you, I really don't know. The situation is still not really much better. Actually, it's worsening. Now the winter is coming, and yeah, so and I don't know what's the situation with vaccinations, etc. But even if there is a vaccination coming soon, this will not change very quickly. So maybe there will be another online conference. Maybe we do a hybrid conference with a limited number of people at a location. Or maybe, if very optimistic, we can really do an in-person event again in middle of next year, but to be honest, I doubt this will be possible. So we can't really announce anything today. There will be a GeoPython 2021 and a Python Machine Learning 21, that's for sure. But I can't tell you a date, I can't tell you anything. So the probability for an online conference is really high. So now it's your turn. We will promote every one of you to panelists. And if you want, you can say something, you can give some spontaneous feedback. While we are upgrading you to panelists, there is a short break, so we will lose the client an instant. And so I stop sharing my screen and we will promote you to panelist. If we do this all together, then it actually works. So there will be a small interruption. Don't worry about that. So we are like a Zoom, a regular Zoom meeting. Actually, we never tried that before. So if everything crashes, it doesn't matter because the conference is over. So the word is yours. So anyone who wants to say something, you can say something. Someone just told me my sound is off. Did we already crash Did we already crash the conference? Anyone say something? Adrian?
No, it seems to work. Seems to work quite well.
I just got a message from Reimer. The sound is off. Don't know what he meant. Maybe his sound is off in this case. So yeah, maybe it was the transition to not off, just much lower. So there was maybe really an issue. So I'm quiet now. It's your turn.
I would like to take the opportunity to thank you, Martin, for organizing this all. It was really, really great. And you mentioned a couple of technical difficulties. I think no one minded too much. It was really great to have you organizing this, and I think it's quite a lot to handle two tracks at once, and you had all this like infrastructure running all the time. This is highly appreciated.
I can actually show you how it looks. Here are the two computers, and here's my other computer. This webcam isn't really movable. Here's my other computer. Here's the screen here's the screen where you are at the moment, and there is also a screen. Here is the schedule. So it's all a mess at the moment. At home. So yeah. Okay, just
you got a nice control center there, like for space travel.
Okay, anyone else? It's your turn.
No, this has been a great couple of days. Thanks very much for organizing. Thanks to all the speakers. It's been really interesting seeing what's been going on. And yeah, a lot more machine learning involved in this year's GeoPython. So that's been really, really interesting. It's been good to see that. Thank you all.
No, I agree. It was like a shift in the program, I think, from the past years, or maybe more a drift. Like from year to year, the machine learning got more and more. Maybe we could get some feedback on if this two-track setup is good, or if someone felt like we were actually missing something because we wanted to see two things at once. It would be interesting to know.
I'm in the matrix.
I think one of the few things was a case of I didn't realize I missed the paper versions of just having the schedule, so I have to like scribble things down and then figure out which session I want to jump into.
Okay, any other feedback, suggestions, things? Don't be shy.
Hi, everyone. I just wanted to say thanks a lot. I think in terms of feedback, we could leverage this sort of setup maybe a little bit better. So right now it feels a little bit like go and talk. But if we had, I don't know, a discussion about a topic, or maybe like use the coffee breaks in this way, maybe that would be an idea for a future online conference. So yeah, in COVID times, I think we have to be creative. So I really appreciate having it this way. And actually, I think there's, quite a lot of potential that comes from it being an online conference rather than having all of the costs and time to travel somewhere. So yeah, I think it's an opportunity. Thank you.
Thanks for the feedback. That's an excellent thing. Unfortunately, in the webinar, we don't have breakout rooms. That's something I would have loved to have breakout rooms, so we can really have something like that. Maybe Zoom will do that. Maybe we switch to another system in future. I don't know yet, but it's excellent feedback. Thanks. Okay, last chance. Anyone want to say something? Okay, if this is not the case, so I would like to thank everyone again. And yeah, maybe see you online again next GeoPython. Maybe we can meet in person next GeoPython. So thank you very much and have a great time and use masks, everything, and be safe. Thank you.